Then Brian. So I need to switch out my comfort moments. Then focus. Oh, okay. So Martin is Zoom. So even if I have the wrong one, straight here. So,
Pois tem uma piada no vai que
yo, ada Zoom. Kama jitase punya ada kana
ah
sa personal tu. Tawa ke bula. Yeah, I am interested because Not bad. Hey, hey, stop it. What are you doing? Zeg, hey, zeg, hoe is je domme? Zeg, hey. Dog, man, Lisa, right here. What's up, dog? What's wrong? Check it out. You know, once a car, when we talking, even before the charging ports in. No, no, you need a charging port properly. I just want to plug in and go. It's the vibe. Huh? How is it? What you say, bro? I'm good, man. How are you? Jacob? The main was here already. Which one? Those in the room. Okay. Oh, yeah, yeah. He was here. You checked in? Yeah. Okay. I imagine ask me so much questions. Good. And he had a lot of questions. And I had a lot of questions too. Did you? Yeah, but this is good. Dit is full block. Ja, full block. I was yesterday in a meeting with this. Okay. But that job. Oh, yesterday, bro. How many days there? Nice. A week. Yeah. On Friday. Hell. It's then on Friday. Weekend. Yeah, so we said we go down. Yeah, because center in my lunch. Yeah. Right. Well, remember, they also probably want to buy it from me to sell it again. Um, and that hard drive vibe and whatever, that's nonsense to get. They just trying their luck. That's the listening to them. Tiny's trying to sell an old laptop. And now yesterday she almost got scammed. I wish it my mom. Don't send it so. What they do is, you know that scam where they send you like a proof of payment and then they send the Uber. You know that scam? Always, they're gonna come, they're gonna send the Uber now. I say the Uber can stay in there, you don't give them that. You don't give them that laptop. Now, my tiniest thing is this. My sister gave her that laptop like 34 years ago. HP, but it was a quiet laptop. It was like a think it was an i7, 250 gig hard drive for my sister. So now what happened was my sister now changed to get a laptop. She told me, look here, you take this one now. So then I said, okay, cool. That's because I'm giving like something now the end of the month, now next weekend. She's like, look, she's gonna sell this laptop. She wanna make like Papa is like, oh, what the hell, you don't have to do that. She said, yeah, but now what must she do with another laptop? She didn't have kids or anything. She understand it. At least maybe she can make a like a Sunday lunch or something, you know what I mean? So I'm like, okay, start selling it. And I mean, that laptop, when you check the prices of it, still like it was like 12 grand, 30,000. Because it's like, I don't even know IBTM's old HPs, the i7s, they were cack expensive over it. So she put it on for like 4,000 rand, or the like three and a half maybe, whatever, because it's still in a fucking good condition. With a bag, um, so the bags, two bags. So it's a laptop bag and it's the laptop backpack, right? For 4 grand now. Now she sent me this message. She said, "Nah, this bra was straight up. Will you consider 3 grand?" I say, firstly, if somebody say ask you that, they're gonna negotiate deal with you. Don't say yes to the 3 grand. Also, he's telling you that the 250 gig is too small. He's pushed because a lot of the new a lot of laptops only come on with 250. That's it. You need to upgrade it yourself. So he's just trying his luck. You know what I mean? I tell him you can take it for 3 grand, no charger, no bags. Tell him that. Tell him you paid 1,350 because that's what we paid. So when was it? End of last year. So before my sister gave it to me laptop. So that one was obviously fucked out the charger. I broke it. Not by drove over it. Fell out of the hey, old bushman. That wow, fell out of the thing. He drove over it out his old driveway. Anyway, so we got the new charger, but the charger was like 1.3, bro. It was the original charger. I tell him then, paid 1,300. And you bought the bags, obviously. So you can take the laptop with 3 grand, no charger, no bags. And the bags are 500. Huh? He did, but I. Because when I was getting this, that is that's good. Yeah, that's Angie. Yeah, you probably don't know it's Angie. You should have like really know them. I told him, yeah, I can put up with more options for the team. Everybody's like be chatting to me and you are shit. To me, it's probably best for me to just get along. So she put on Ashburn and check all over the place. Yesterday, last year, they put that fucking so it's simple. They send the approval and fuck so that phone. Approval payment. They're gonna send the Uber. But I tell her she was about to give that and I said you were waiting.
So I'll just give an extra minute because I see people coming from the poster session, and then we start. Okay, so I think the flux into the room has more or less stabilized. We get more people as we go. So just very quickly to start, I would like to thank the presence of everyone here and also all the speakers. I would also like to thank the IAU, and in particular divisions B and D, who supported this meeting. And it's very important for us to have the possibility to present the field and discuss this field of gamma ray astronomy, in particular, ultra high energy gamma ray astronomy, which is an emerging branch in ground-based gamma ray astronomy. So the Cherenkov telescopes are very well diffused in the astronomical community, I think, and all the expectation with the large Cherenkov Telescope Array Observatory is also very well noted and expected by the astronomical community. But there is a particular branch in ground-based gamma ray astronomy which deals with energies that go up to the PeV that has really achieved its breakthroughs really in the last few years, particularly with the work of Lasso and Hawk, and is a field that's very promising. And the purpose of this focus meeting is really to bring awareness into the IAU and the astronomical community at large of the capabilities, the potentialities, and what is about to come in the future from this field. And also highlight the synergies and the scientific potential that it can have in interaction with other IAU or other astronomy areas. So again, thanks a lot for everybody to be here. This is going to be a two-day meeting. We have made an excellent lineup of speakers, I think, that we're going to talk both about instrumentation, given a general perspective of the field, and the various science areas that we excel in this research area of astronomy. And it's my very great pleasure to start this meeting introducing Hazmik Mirzoyan from the Max Planck Institute for Physics in Munich, who is going to present us in the first half an hour of this meeting a historical overview of this emerging field. Thank you very much, Hazmik.
So, good morning, ladies and gentlemen. I hope you will enjoy for the next half an hour some presentation about compressed presentation about the history of ground-based gamma ray astrophysics, and I will try to give you some glimpses in this condensed information. So let's go. Yeah. So all of you know the birthday of cosmic rays is considered 1912, when Austrian scientist Victor Hess discovered this penetrating radiation coming from outside, from space. Something like 20 years later, 24 years later, I think he was awarded, together with Anderson, a Nobel Prize in physics. And then I think you know the story. It was very interesting. Anderson, I think, deserved a Nobel Prize for discovery of positron, and then they remembered positron was discovered in cosmic rays. So Anderson and Victor Hess got a Nobel Prize. So this is a beginning of our discipline now. The spectrum of cosmic rays is well known. You see something like maybe 15 to 20 experimental measurements of cosmic ray spectrum, stretching from a GeV to over 10 to the 20 electron volts. And then intensity varies in a large range. So mostly we measure positive charge coming from space, but also I think we measure something like 50 times less electrons, even less positrons, antiprotons, and so on. So, and then when you look carefully into the spectrum, you see that there is some structure there, and then the structure became a matter of research by itself, like the knee problem, ankle problem. So I'm not going to dwell on it here. We are doing cosmic rays by using neutral particles, which are gamma rays and neutrinos. Because if your instrument is able to measure neutral gamma rays, you can pinpoint direction to the source. And then you can try to measure the spectrum, and you can try to judge what kind of mechanism at work in this source. I did not really count, but I think for the time being, there are roughly about 300 sources known of which are emitting gamma rays at very high energies. And when I say very high energies, I mean everything above 20 giga-electron volt. And then this number has a real boost in the recent few years, essentially because of the Hawk and Lasso instrument, who found number of several dozens of pevatron sources not known before. So now let's try to go to the beginning when things began. You know. Most of you, I'm sure, remember from the university course in mathematics the name of Oliver Heaviside. And then he was the first one who calculated and predicted the main features of a special emission when electron moves in a transparent medium with a speed higher than that of light. And then while he was working end of 19th century, it was not known that the speed of light is the highest speed known. So this is a typical work of a genius who advanced his time by half a century. And it was, of course, not appreciated by the contemporary scientists and was forgotten. And 50 years later, suddenly people said, this is what Oliver Heaviside meant in the past. So in 1912, he calculated geometry and the angle of emission relative to the axis of movement of the charge. While he has published, you see, the references are given or shown for the 6 years when he published 6 papers. So this was the time where people believed there is an ether, and then 1881, I think, experiment of Michelson-Morley put this ether problem as problem number 1. I find similarity to the problem of dark matter now. Ether problem was solved by Albert Einstein, 1905, with the special theory of relativity. And for me, the situation is very similar. We are waiting for the next Albert Einstein to come and then to explain us what is this dark matter, what people are looking everywhere. So and then it is interesting to mention that also Arno Sommerfeld, many of you may know Sommerfeld was a professor of physics in Munich, Germany, and he was a Geheimrat, in the government. I think he also calculated some problem. A charge is moving in a vacuum with a speed with a speed higher than the speed of light. Again, 1904, it was not known that speed of light is the highest known speed. This was not possible in a vacuum, but if there is a medium with a given refraction index n, then I think his equations were giving a valid solution, and then one can follow the sonic boom. I think it's a quite thick article, very detailed one. Yeah. Coming to experimental side, I think the oldest thing that are left mentioned in the literature, it comes from the daughter of Marie Curie, who wrote about her mother, that Marie Curie, by sometime in 1910, I think, when she used to go to cellar, she had a lot of bottles with radioactive salts, dissolved in distilled water, there was a bluish glowing. So, and then because Marie Curie was looking into fluorescence, luminescent fluorescence, she thought it's another type of fluorescence. She did not pay attention, but the first mention goes back to this time. Yeah. Then I think we should mention the French scientist Mallet, who published 3 articles on bluish glow in a transparent liquid. And then these 3 papers are dated between 1926 1929. And then on the left, you can see one of the papers. It's essentially 1.5 pages. And this is how the paper was looking like 100 years ago. Some papers, yeah. And then the important thing is, I think Mallet recognized that the spectrum is continuous. This emission spectrum is continuous. And this, of course, does not go in line with the luminescence or fluorescence. But somehow he failed to offer deep explanation of the effect. He gave a description of the effect. Next, important person to investigate this problem was Pavel Cherenkov, who was born 1904 in a poor peasant family with the name Novaya Chigle in Voronezh province, somewhere a real province in Russia. And he studied in Voronezh State University. In 1930, he became postgraduate student of Sergei Vavilov at the Institute of Physics of Soviet Academy of Sciences in St. Petersburg. Later on, this was called FIAN, Fyzické Institut Akademie Nauk. He had to find the fluorescence nature of solvents of uranium salts emitting bluish light. But then I think the curious PhD became surprised when he saw that there is emission also in pure solvents. Even in water, there was an emission. Yeah? So, at some moment, I think Pavel Cherenkov became desperate because I met a lot of people who knew him in person. And I met him practically every day during my PhD time, queuing in the canteen in the Lebedev's Institute. So he was not talking to nobody, but was a very silent person. But then when he was young, he became desperate because his colleagues were teasing on him. He was sitting in the cold cellar without heating, without light, many hours for accommodating his eyes, and this was the measuring instrument. And then his colleagues meant he's hunting for witches and so on, so he became desperate and formally complained about his boss, about the director of the institute. And then I think there was a long process, and then the institute could convince him that, in fact, he can make a PhD thesis with this topic. It's not a nonsense. So he continued. And essentially, I think 1937, he measured a very important part of this emission. He measured that the emission is anisotropic. It goes in the forward direction. So it's not isotropic emission. Before that, 1934, he published a paper where he described the main features of the emission. And then he offered his boss to become co-author of the paper, but Sergei Vavilov declined it. He said, no, you did the work. It's your paper. And then the boss wrote his own paper, and butt to butt, they published in the same journal, Produfian. And then Sergei Vavilov, being an educated person, he thought, what physical effect could produce a continuum spectrum? And he thought it's a Bremsstrahlung. So in his paper, it's claimed this is a Bremsstrahlung effect. In reality, this was a brand new effect. 1937, Cherenkov sent this article for publication to Nature, but Nature declined his paper because they said very strange white mouse, kind of from somewhere in a deep province in Russia, and made a big discovery. So they declined his paper. I don't know if Nature behaved like this today, but becoming desperate, I think he sent his paper to Physical Review, and Physical Review accepted his paper, and this was the official birthday of Cherenkov light, Cherenkov astronomy. I think the effect carries his name. So, and then looking to this picture, I think you know very well this bluish emission, in the water. This was one of the first things when I was in a sixth semester, and I was taken to a reactor near my institute, and then suddenly I saw this very intense bluish emission in the water. I was told that there is no light source, it's just by itself. And then I think it had a very deep impact on me. So I think, still I think that impact, I think I have in my memory. So there was a famous scientist, Nobel Prize winner, Blackett, in Great Britain, who in 1948 calculated emission of light by the night sky. And then he calculated that there should be some 10 to the minus 4 effect due to elementary particles from air showers which were discovered in 1938 by Pierre Roget. And then going to visiting his colleagues, younger colleagues, Gelbert and Jelly, who were measuring the Cherenkov effect in water, he told them, there should be also effect in the air. And then next day, Gilbert and Jelly started composing a very simple detector. You see the picture here, putting a small mirror and to each photomultiplier in the focus. And then they experimented 1 year and discovered light pulses are coming from the sky at a low rate, something like 8 pulses per hour. But this was the birthday of Cherenkov effect. So when looking back, who talked about gamma ray astronomy, then two names are coming to mind. The first name is Philip Morrison, 1958. And then the second name is Giuseppe Cocconi. And Giuseppe Cocconi went a little bit further than Morrison. And he said, make a simple instrument that can measure at 1 tera-electron volt. And then you will measure a huge signal from the Crab Nebula. And the signal to background ratio will be 1,000 to 1. So you will immediately measure, and then a lot of people got affected. This was at the Cosmic Ray Conference in Moscow. And then I think since that moment, a lot of people started very intensively experimenting. So this is a cartoon of extensive air showers, and these extensive air showers could be measured from space. They could be measured on ground by different types of detectors, moving detectors like telescopes, not moving detectors. We will see them a little bit more later on. And these cosmic ray showers are looking like this. On this cartoon is shown a gamma ray shower and a proton shower and then iron shower. And then just you see that they look, their emitted light is comparable, but they look very different. So it's very clear that there should be a means to differentiate them. Gamma rays interact in the atmosphere, starting an electromagnetic cascade, but hadrons, like protons and iron, they start a nuclear cascade, and then you see the nuclear cascade has many branches, producing multiple of pi zeros, pi plus, pi minus, and then the pi zero will decay into 2 gammas. So also hadron shower will have an electromagnetic branch. So I think these are general issues to know. And then in a simplified way, you can say if you measure air showers on the ground, then you have the following picture. Imagine these are kind of detectors, scintillator detector, or open photomultipliers which measure Cherenkov light. And then the air shower is coming, a particle is coming and produced air shower. And this is a snapshot of air shower. And then you can see, I think, the front of air showers. And then particles are always faster than light, because only under that condition there is Cherenkov light emission. In a transparent medium, air, where the refraction index is slightly different from 0, on the 4th place after comma. So first are coming the particles and Cherenkov light, and this is a function of distance from the shower axis. Yeah. And then if you have Cherenkov light detectors, you will measure Cherenkov light. If you have particle detectors, you will measure particles. So and then this size of the, let's say, front size of the air shower, conditionally we can talk about 150 meters at low energies. At higher energies, it could be significantly larger. So now I I think with this composite slide, I would like to show instruments which were built immediately after this declaration of Kokoni. And then the first and the largest instrument was built by Chudakov in Crimea. And then essentially, I think the story says that Chudakov was experimenting on Tianshan with 8 mirrors since a few years. And then I think he decided to start the gamma ray astronomy and took these 12 searchlight mirrors. Each one is 1.5 meters in diameter, and made a tracking system. And then you see there are 4 branches. Every 3 telescopes are connected rigidly to each other. And he has experimented between 1959 to 1964 in Crimea. And then similar experiments were produced by John Jelly, United Kingdom, and then by Neil Porter in Ireland. You see their instruments are much smaller compared to what built Chudakov, but the results were maybe to a certain level similar. These were experiments. After 5 years of experimenting, Chudakov did not manage to measure any measurable signal. So he became very big skeptic, and then he became big boss in science in Soviet Union, and he did not believe that there is such a science as gamma ray astronomy. Until 1988, where Trevor Wicks told me when he discovered the 9 sigma signal from the Crab Nebula, and he met at the conference Chudakov, the first thing he did, he approached Chudakov and said, "You see, I measured 9 sigma, and then you said long ago that I will never believe any signal below 6 sigma. I measured 9 sigma." And Chudakov said, "I regret that I did not put the threshold 10 sigma by then." So then I think another important step was when people measured the shape of a shower, which emit into intensifier. And then these were a series of experiments by David Hill and Neil Porter in 1960s. And then you can see a simple telescope. It's a Schmidt telescope, 25 centimeter diameter, half mirror image intensifier. And then they were shooting photos here at the output of image intensifier. And there was a simple photomultiplier here, which was giving a trigger to this system. And in this way, they saw these elliptical images already in the beginning of 1960s. And at this moment, and then when they were triggering the system randomly, they could see only the stars. So I think they understood some very important message. They understood that this image shape is changing its shape and the distance depending on the impact point of the elementary particle. So, and then they understood some very, very primitive but very important message. If you will make a photograph of the same shower with 2 types of telescopes, then you can find the cross point, then you can find the impact point. So then I think there was Josh Grundley. He was looking to some fancy stuff. Instead of 1 photomultiplier, using 2 photomultipliers per telescope. And then Mount Hopkins and in Arabri, he was experimenting 1970 to 76. And then inclining 2 photomultipliers towards each other. And then with little bit fantasy, he was imagining that maybe lower part, if you look at photomultipliers, you look to the lower part of the shower, they measure light from the muons, and the top part, they measure light from air shower. And in this way, he was doing some kind of little bit magic, in my impression. And then he claimed, already he has a very interesting paper, just as a matter of fact, he thought he discovered pulsations from the Crab pulsar, but there was no DC emission from Crab Nebula. So I think this was one of the many papers which turned out not to be correct later on in time. But this was the time when explorers believed in all kinds of magic. On the other hand, I should mention that 2 photo multiply instead of 1, it's already kind of image, it's a little bit more than 1. So, this is an array of Earth-Cherenkov telescopes proposed 1984. This was not yet an official science. I think at a NASA workshop in Baton Rouge, 1984, by Trevor Wicks and Trevor Wicks, and this is the first configuration that later on was adopted by Veritas. Although later on they reduced number of telescopes to 4. Yeah, so they understood very clearly the power of multiple views, and then you see they were talking 7 and 15 meter aperture atmospheric Cherenkov cameras with a spacing of 75 meters. So then I think this Mercedes type, I think Cherenkov telescopes were tried by Ted Tarver in Great Britain. So I think I will not stop on this. But people understood if you measure a cross point of several shower images, then you can do very powerful image analysis. Some key developments I should mention: in 1780s, there were plenty of discoveries on a 3-4 sigma level. So everyone who used to go to a conference, they were reporting their sources. And I have a feeling that it was a shame if you go to conference, you don't have your own source. So everyone is reporting some source, and then you say, oh, I do have my sources. And then if you look to conference proceedings long ago, it's full of discoveries. So on the other hand, I think these discoveries turned out not to be correct, but they keep the science alive. So and then people are working in this direction. And then one of the major things what happened, I think, is when Michael Hiller suggested parametrization of image shape, 1985 in La Jolla. And then by using this technique, people 10-meter diameter telescope discovered 10 sigma signal from the Crab Nebula. I think Michael Hiller formulated it very nice in his paper about the development of gamma ray astronomy. He said, a physicist apparatus gradually learns what is expected of it. So it's blame the apparatus for a dog-like desire to please. So you report some signal, yeah. Your instrument likes you also. So. Okay, this is Trevor Wicks, and next to his 10-meter diameter Whipple telescope. And then this is the historical telescope. At first, they measured 9 sigma signal from Crab Nebula. Then a little bit later on, they improved it to 20 sigma by better improved camera. This is the birthday of gamma astronomy. I was involved to building some such telescope. This is the first prototype telescope I think our group built in 1989 in Armenia on Mount Aragat. And then we were building 5 such telescopes. But then I think economic situation became complex, and we moved to Canary Islands with our German colleagues and Spanish colleagues, and we built a Hegra instrument. You see 4 telescopes out of 6, which operated on the Canary Island La Palma between 1992 and 2002. And this instrument clearly showed the power of multiple telescope observation, which people dub as stereo. So a number of sources were discovered, something like 10, and then people understood there is much more. And then we switched to larger telescopes. So I think I just mentioned, showed some milestones of that time. Detection of Crab Nebula by Whipple telescope, second generation telescope who showed this stereo principle. And then the third generation was one of the third generation telescope was Magic, who in the first time went from 200 GeV down to 20 GeV energy, like discovering the Crab pulsar, and the energy is above 20-25 GeV. So these are these 3 telescopes. Veritas has Magic, and then the first 23-meter diameter telescope of CTA. We will see it. This is Veritas in Arizona. near Tucson, and then in the background you see this Schwarzschild telescope, 9-meter diameter. This is a 2-meter telescope. Yeah? These are 10-meter diameter telescopes, 12-meter diameter telescope, 4 of them. And similar design has a HES telescope in Namibia, and they have a gigantic telescope in the middle, 28-meter diameter telescope. So I think this is another very famous instrument, just in the neighboring country, Namibia. And this is the site of magic. Here you can see Magic 1 telescope, and then 17-meter diameter, and the Magic 2 telescope, 17-meter, and then in the middle you can see the first 23-meter diameter LSD telescope, CTA LSD telescope. So now it looks a little bit different, this location. Just to mention something very important in my mind, I think why do we talk about Cherenkov effect so frequently? The reason is it is extremely intense emission, extremely intense in my impression. So you see, for example, number of photons emitted, number of Cherenkov photons emitted is changing between 16 kilometers, let's say, and then sea level between 4.5 to 45. So something like 10 photons per meter. Imagine electron is traversing 10 kilometers. 10,000 times, let's say 10 photons, 100,000 photons will emit just a single electron. Yeah? And then if you have 1,000 electrons at 1 TeV, then you have 10 to the 8 photons. So it's a very intense emission. But if you will go to water or to ice, then I think intensity will be even 1,000 times higher. So this is a very intense emission, and that's why it's so comfortable to use and very powerful. This is how light is, I think, from a single muon, simulated muon comes to the ground, and you see there is self-focusing effect at about 120 meters. This is the so-called hump. Yeah. But typically, I think a muon will produce light like this until 120 meters. And then I think a large Cherenkov telescope is 100% efficient to measure muons until 120 meters. With 100% efficiency, you measure all muons. And with this cartoon, I try to explain how this cigar-shaped image is stemming, because it's very simple configuration. A single particle, for example, a muon traversing, it creates a ring of, between two heights, it creates a ring of Cherenkov light. And imagine your telescope is here. So your telescope just catches up from this ring amount of light, which is proportional to its reflector area. So, and then it is under this angle phi. So, and then if you make this cartoon, I think this is explained in this paper, yeah, then you will see that from every height, because Cherenkov angle is changing, you have arcs. When do you connect all the arcs together, you get this cigar-like shape. So this is interesting to follow. But the most important thing why we are able to do this astronomy is just because of one fact, because our atmosphere has exponential distribution of refraction index. If you do it in horizontal direction, you will not have this situation. The refraction index is the same. So this display and then cigar-shaped like image is due to exponential atmosphere. Image shapes, you see the typical image shapes, these cigar-like shapes. For gamma rays, I think you can nicely fit an ellipsoid, but if it's a hadronic, you see it's fuzzy and it has a very undefined shape. So I think by using these differences, you can reject from 5,000 images, you can reject 4,999 while retaining one gamma ray. So I think it's a very powerful technique. And then if you have few telescopes, with few telescopes, you do a better job. You can define the impact point of the shower. And then what we are doing in our science, we are trying to see with the simplified mechanism, if from a given source we see some such two spikes, let's say synchrotron self-Compton model, for example, yeah, inverse Compton model, then we are inclined to say maybe leptonic mechanism is at work. And if we measure this Sugarloaf type spectrum, then we are inclined to say maybe hadronic mechanism is at work. This in a pure way, I think this we measure very, very rarely. And then it's a mixture. So I think this is an ongoing activity. A few words what we measure. I think we measure, for example, Crab nebula in gamma rays and Crab pulsar in gamma rays. This is the pulsar within the nebula. Nebula, I think, this is a picture from Chandra, evaluating this source in a great detail. This is our calibration source. In recent years, I think it became clear that Crab nebula is also Pevatron. I think we measure gamma rays till the energy of a peta electron volt. Yeah. I cannot stop there. I think there were multi-messenger observations on flaring blazar coincident with high energy neutrinos from this IceCube event, 170922A. And then a lot of collaborations participated in this work. And then I think this was considered one of the first multi-messenger events. Or we measure GRBs with the Cherenkov telescopes. I think up to now, something like 5-6 GRBs are measured by Cherenkov telescopes, and a gigantic GRB has been measured by LASSO 2 years ago. So I think we are part of multi-messenger and the multi-wavelength astronomy, and then indispensable part. And then this information, unique information, comes from several instruments. I want to mention a few words about HAWK, which became one of the very productive instruments in ground-based gamma ray astronomy. The HAWK instrument is located at a height of something like 4,100 meters in Mexico. And then you see one photo of these big water tanks. Essentially, HAWK is measuring, in my understanding, the image of the air shower on the ground. And then particles enter these electrons, positrons, and muons enter these water tanks. They produce the light in water. And then based on this picture, I think HAWK does a very interesting gamma ray astrophysics. Similar instrument, larger one, is LASSO. LASSO is employing four types of different detectors. Largest detector is a surface array, so to say, which with this scintillator detectors, I think over 5,000 spread over 1 kilometer square. But they have also underwater muon detectors, and then they have underwater pools like HAWK, something like 3.5 times larger. I think LASSO became one of the major instruments. What is interesting to note about LASSO, this is at above 4,600, I think at 4,400 meters above sea level. You see there is a lot of water there. So I think our colleagues were smart to use rivers on the mountain in order not to carry water from down the cities, let's say, and then this reduced the cost of the instrument. Because I remember I was impressed when I learned that roughly half of the cost of HAWK was carrying the water to the mountain height. So a few words about Casamia. This I would like to mention. Many of you may not remember, younger generation, but in 1990s there was a huge array built by I think a team essentially from Chicago. And this detector was operated in Dugway in Utah at a height of 1,450 meters. And then Jim Cronin, Nobel Prize winner, he was the PI of this experiment. And then this instrument consists of two major parts. CASA, which was a 0.23 kilometer square detector. Yeah? This is an aerial view. And then MIA, which was an underground detector with 2,400 meters square. So if you divide this 2,400 to this 0.23 kilometer, you will get a 1%. So muon active area was 1%. And then the size of this was 1/4 of today's LASSO. So and then what LASSO did, LASSO increased the total area of this detector from 0.23 to 1 kilometer square, but increased essentially the muon coverage to 4%, from 1% to 4%. And suddenly they found a huge bunch of pevatrons. I think LASSO produced, I think, over 40 new pevatron sources, not known before. And then you see the irony of the history. If Jim Cronin would have, instead of 1%, decided to 4% or 3%, maybe they could have discovered pevatrons 30 years ago. Anyway, this is how it is. Next generation instrument is CTA. Probably we'll listen more about it. And then I think most astrophysicists from all continents are part of it, over 1,500 colleagues. And then there will be two locations in the southern and northern hemisphere. In northern hemisphere, this is the first LST taking data. This is 23-meter diameter telescope next to MAGIX. In northern hemisphere, I think is also built the ASTRI instrument in the next island to La Palma. I think Giovanni Pareschi is sitting there. He's a PI of ASTRI. 9 telescopes, 4-meter diameter. We will listen, I think, very soon about completion of this array. And then this is a picture shown recently at a meeting of LSD's CTA collaboration meeting in Prague, end of May. This is how the array will look like in 1.5 to 2 years from now, to MAGIX and the 4 23-meter diameter telescopes. On the next island, we will have ASTRI. So I think this in the north, we will have a cool array just within 2 years. In the southern array, people should build it. And I came to my conclusions. So gamma ray astrophysics is making gigantic progress in the study of highest energy phenomena in the universe. And the relatively recent addition of particle arrays such as HAWK and LASSO, and in near future also SWIGO, will allow to combine their very high sensitivity. These instruments they are not moving, and they absorb 2,000 hours, any source within the field of view, compared to Earth-Cherenkov telescopes, who can measure 200 hours per year. Yeah. And they have very high level of background tagging, something like 10 to minus 4, 10 to minus 5. They can reject background or they can tag the background. And then if they combine, in the moment when they combine it with 4 to 5 times higher angular resolution and very high sensitivity of IACT technique, and then this will be CTA CTA North and South. And also, I think, I don't know, but if it is announced, but colleagues from LASSO are started building 32 IACT, 6-meter diameter. They call it LACT, yeah, LASSO IACT. In China, they will complete it, they should complete it in 3 years. So such a combination will be of utmost importance for observing universe in the energy range from 10 GeV to 10 peta-electron volts, maybe even somewhat higher. And this will become the indispensable part of multi-wavelength, multi-messenger observations of the universe for at least for the next 30 years. Thank you for your attention.
Thank you very much, Hasmik. We always learn a lot from your historical overview. Thank you. So perhaps time for one question from the room or from remote before we move ahead. No one? Okay, so thank you very much, Hasmik. And let's proceed with the session. Yes. Now we're going to hear from Alberto Caramignana about the HAWK Observatory that Hasmik just introduced to us.
Thank you very much for the invitation to give this talk and tell you about the HAWK Gamma Ray Observatory that we built in Mexico. All right. Okay, here you can see the HAWK Observatory, which just mentioned that is 500 meters below the Large Millimeter Telescope Alfonso Serrano, which is part of the Event Horizon Telescope. And it allows us to basically build HAWK because there was already infrastructure here. So I'll tell you very quickly about the collaboration, the site, and the observatory. This will be just 3-4 slides. Then I'll go deeper into our results from the HAWK Observatory, and just at the end, a couple of slides about the future of HAWK after these 10 years. So this is the HAWK collaboration. When we met in Puerto Vallarta, our first really relaxed meeting after the COVID pandemic, so we were all very happy. The HAWK collaboration was built in 2007, basically from US and Mexico scientists, just from the Milagro collaboration, together with Mexican institutions. And nowadays it also has institutions in Europe. and in Asia here. This is a view from the airplane when you go from Houston to Puebla. Puebla is like 120 kilometers east from Mexico City. And then here you see Pico de Orizaba or Citlaltépetl, which means mountain of the stars. That's the highest mountain in Mexico. Here you have Sierra Negra or Tliltépetl, which is the dark or black mountain. At the top is LMT, the Large Millimeter Telescope, and the valley here is at 4,100 meters. That's where we have Hawk. It's 7 kilometers from peak to peak at the latitude 19 degrees. So this is what we built. Is, as explained, is a 300 meters, 300 water Cherenkov tanks, large volume, 7 meters diameter, 5 meters height, almost 200,000 liters per tank, and that you multiply by 300, so almost 60 million liters of water. 150 meters, so that makes a physical area of about 22,000 square meters, and the detector area, 40 meters per tank, gives you that we have a coverage close to 60%, a little bit less, effectively in the dense array here. Basically, we record 25,000 events per second, so that makes 2 terabytes per day. So we're already in the petabyte regime after 10 years of running. Field of view, more or less 45 degrees, just to take a number, a bit less, bit more. So that takes us to the south to minus 26, with minus 27 being the galactic center. Basically, we cover 1/6 of the sky permanently, and it's a transit instrument, so we scan 2/3 of the sky every sidereal day. We work day and night. August 2013, a little bit after the photograph that Rasmik showed, with 111 tanks, we started partial operations. With once we completed the array on Equinox Day 2015, almost 10 years ago, we started full operations. And since 2013, we have a duty cycle of 92%. Funnily enough, our best year was 2020, when some people say that we left, there were no humans really bothering the instrument and it could run by itself. It runs automatically, of course, and we just monitor it on the distance. So that's a couple of graphs about the performance of Hawk. So this is basically the effective area versus energy. Here is 1 TeV. And we just moved from our PAS4 reconstruction software to PAS5, which gave us a boost. This is for different inclination of the showers near zenith and near 45 degrees. And also the PAS5 software has improved our energy resolution, particularly once we reach 10 tera electron volts. Okay, so let me go into the results. So I did this graph about our paper metrics, not that we all love having these paper metrics, but basically we have published so far 74 papers since 2012. And you can see basically 3 groups of papers. That's what I like here. So 100 authors here, and the vertical axis is the citations. 100 authors is a typical for Hawk paper. That's the left side of our collaboration, a bit more. So these are the Hawk papers, different degrees of citations. We have papers here, like 7, 8 papers with all the collaborations, IceCube collaborations for multi-messengers, papers with Veritas, and papers with HESS. I'll show one with HESS. And we have these 2 outliers, which make 4,000 of our 7,000 citations. So when you calculate my H index, for example, you should remove these 2 because it's a bit cheating. But these 2 are good examples of what you get when you participate in multi-messenger work. Because 3,000 authors, 3,000 citations is the merger of the 2 neutron stars in 1708-17. where Hawk provided some upper limits on the emission in the tera electron volt range. And then the other one is the neutrino PLAC coincidence recorded by MAGIC. So MAGIC saw it at the GeV range, and Hawk reported an upper limit at the TeV range, both for just after and before the transit, and another one for the whole database, so from 2013 to 2017. Okay, so I'll show you a couple of examples here and then some of highlights of our main papers. So this is a nice work with IceCube. And this is on cosmic rays, is a measurement of the cosmic ray anisotropy over basically all the sky. And this can be done because IceCube has this iStop array for cosmic rays, and in yellow is the sky coverage going from the south, equator at 0, and the north at 1. In terms of the sinus of the declination, IceCube covers all the yellow range to close to the horizon. And then there is a good intersection with Hawk that help us to calibrate more or less our ranges cross at 10 TeV. And this is a coverage from Hawk. So basically 95% of the sky coverage, which allow us both to measure large scale anisotropy. And on the right, you can see the low scale anisotropy. At 10 TeV, these particles have a gyration radius more or less on the tens or hundreds of astronomical units. And nicely enough, this hotspot, matches more or less the Helio tail of the seen from Earth. Okay, this second paper in collaboration was with the HESS collaboration. So you can see 4 maps of the galactic plane. HESS has made this very nice galactic plane survey from the south, and Hawk does naturally a galactic plane survey from the north. So on the top is the HESS data as taken for a certain latitude range, galactic longitude range. And on the bottom is the Hawk image. As you see, HESS has naturally a better resolution, angular resolution. And the analysis, the comparison, they degraded their signal. Basically, they mimic in terms of energy and PSF resolution what they would see if they had a response like the one of Hawk. And we made a comparison here. 4 particular regions are checked here. And as you can see, there are some advantages that even when they mimic a response, Hawk can see things that are not so obvious in the HESS data. Particularly, our response to extended sources is better than in the case of Cherenkov atmospheric telescopes. Okay, so let me get with a handful of Hawk results. So this is our third catalog. That's one of the most cited papers, not the most cited paper. And as you can see, we clearly see the galactic plane. Our more northern sources, like here, is a boomerang at plus 62 declination. And this map doesn't show the galactic center, which is like 4 degrees below the cut here. And the galactic center is not in our third catalog, but it might come here. So you can see the Crabben anticenter region with IC433. That's a typical supernova expansion nebula, and Geminga monogem and 2 extragalactic sources near the 2 closest marker PLAC that we know of. So the Crab Nebula is stable in our energy range. Is that the pulsar wind nebula that we see, and it works very well for calibration. Hawk basically detects every single transit the Crab Nebula at the 5-6 sigma level, so it's a good source to play with. So we have 3 papers. One has just been accepted, PAS 5 paper. So this is from the FJ from 2019. So this is the sampling of showers with Hawk, and basically fitting an ANKG profile. we use to estimate now the energy with basically the intensity of the shower at 40 meters from the core. So that's a ground parameter that's similar to what OJ does, different size, of course. And we also bin this data and use this input in 20-meter rings for a neural network estimation of the energy. And they match pretty well. You can see the reconstruction with the ground parameter and the neural network images of the crab in this paper. Okay, this is our most cited paper, in fact. The discovery of the TV halos around Geminga and Monogem. Both have a middle-age pulsar. Here is 0656 plus 14. These are on the 30,000 year scale, more or less. And basically, what we found is this very bright halo, several degrees on the sky around both of the sources. They are adjoint, so this is basically one single image. And basically, what we found is that the diffusion of electrons and positrons from the emitted from the lifetime of these pulsars is diffusing slowly, more slowly than expected. So they accumulate there, and it gets to be very bright, more or less at the energy of TeV. So here is a schematic view. The ones that are 100 TeV, they die, they radiate too quickly and don't diffuse very far. The ones that are low energy, basically they diffuse too slowly, and this size is optimum at say 1 TeV, and that's more or less a 3D view. These are nearby sources, that's why we see them that big. Now, a nice result that's more recent is the finding of cosmic ray production. In fact, this is hadronic cosmic ray production in a star-forming region, that's in the Cygnus region. Basically, the Cygnus region, there are plenty of sources around here. We had to remove two sources, the Pulsar Wind Nebula here and Gamma Cygni, which show bright in our images. Once you remove your next brightest source here, matches very well this region in Cygnus. This is an infrared image where you have plenty of very large O and B stars, and basically the modeling is a collision of their winds generating shocks that produce high energy particles and gamma rays through hadronic production. This is a spectrum that goes beyond 100 TeV and is fitted with a hadronic model. And then we have performed an AGN survey. Of course, at the TeV range, you cannot go that far. So basically what we did is we selected around 138 sources from the 3FHL catalog from Fermi. Those that were redshift less than 0.3 and that would be within 40 degrees of our field of view. So that makes 138, in fact. Well, 130, yeah. Two are the Markarian sources, who were removed because one is basically here on top of Markarian 501, so it's noisy and whatever. So this is a distribution of the test statistics for each of these sources. Basically, we fit a power law index 2.5 with the EPL attenuation and just calculated the normalization. So we had 1 degree of freedom. So the random expectation is that you get a Gaussian. We have, of course, two outliers, Markarian 421, Markarian 501. But then in the joint distribution, we have slightly tends to be to the right, especially the green sources, which are TeV detected according to the 3FHL catalog, and where you have things like M87. So this has improved. Our student, Fernando Ureña, has a better histogram with more data and past 5, and you can check this poster 1149 to see. And last, not least, we detected a very nearby source. It's called the sun. And basically, it's tricky because the sun makes a shadow of cosmic rays, and the shadow is not very clean because of the magnetic field of the sun. So we basically had to pass these cosmic ray data through our gamma hadron cuts, and then get a gamma ray image, remove the background with knowing that we have a hole here, and basically we have this excess. And more or less as expected, this is our spectrum, this is Fermi-Lat, and then on the right you have the power law fit by Hawk. So 6 years give us a detection up to 3 TeV with an upper limit for energies above 3 TeV. And we don't detect it in the solar maximum, say within the 5 sigma criterion, and we detected brighter emission in the solar minimum, which is more or less what Fermi sees, and that's because of the cosmic rays interacting in the solar atmosphere. Okay, I couldn't talk to you about our 70 papers, 10 our dark matter searches. I regret to tell you that we're empty-handed on that, more or less like everybody. But we have several things like binary systems. Our paper on S4433 in Nature, it's one of our top citations. We have sources a little beyond 200 TeV with we were trying to extend these a bit more, cosmic rays, etc. And there is one paper where they detect the sonic boom of this volcano with in cosmic rays, changing our rate of detection of cosmic rays. That's just for kind of fun paper. We were already looking forward around 2018. We knew that we were going to get some big competition. So we expanded Hawk with a sparse array of smaller tanks. These are 2.5 ton tanks of water, 2 meters more or less, 345 of them around Hawk to expand to, say, 100,000 square meters. If you put that next to LASO, it looks small, but it's big, really. And that is, we're working on incorporating the data from this sparse array with the central array to make our PAS5 reconstruction. So we're entering the future. We were originally planned to operate for 10 years. 10 years, that's March 2025. We have another obstacle, which is that we are in national park, so we have permit to run until February 2025. So we're extending that. Of course, we want to run together with LASO, and also we would like to run together with SWGO within a scale of, say, 5 years. So basically, we're trying to get one is requesting the permit to stay on the site. Obviously, it's not easy to remove this if we were to. So, and also we're seeking extended funding with the good thing that Hawk is in fact cheap to run. And basically, we are renewed part to apply for funding our science case. So Galactic Center is one thing. We will have data for a full solar cycle, and of course follow up. And that's basically because accumulative science leads you that far. And you know, LASO was not only is bigger, but they seem to be luckier. You know, they got this really nice GRB just on top as they were running. So even if we didn't get it, it gave us an argument to run longer, because there is a 1 in 6 chance that it will land in any of these detectors. So if this is turned off, then you don't see it. So that's a reason to keep going. Thank you. Bye.
Thank you very much, Roberto. So time for a quick question. So if no one in the audience, I would have one. So can you say something about the results that were already brought or are coming out of the tended array with the outer tanks?
Yeah, we've been running now for a while. We have the data, but it's been tricky really to incorporate the data of the two arrays. Here it's not seen, but this is a very flat array, just with a gentle slope, but there are like 15 meters this slope here, uneven and 50 meters down here, so that it's been trickier. But we're more or less getting there, and that's our past 6 reconstruction that we want to get more or less some of that data to feed to the NSF for the extended funding.
Thank you. So let's then thank Alberto again and move to the next presentation. And that will be a remote presentation by Hao Zhou from Shanghai Jiao Tong University, and he's going to present us the LASSO Observatory. And thanks, Hao, for connecting at such late time.
Okay. Yeah, thanks. It's actually like perfect time for me, so it's fine. So, 1 second, let me find my screen to share. Sorry, 1 second. Not sure if we are looking at the correct screen. Are we?
Yeah, we can see it.
Oh, sorry. You can. Yes?
Yeah, that's good. That's good.
Okay. Yeah, thank you. Okay, thank you for the invitation and good morning, everybody. So on behalf of the LASSO collaboration, I'm happy to present a brief introduction to of the LASSO Observatory and some recent highlights from our experiment. So yeah, LASSO stands for Large High Altitude Air Shower Observatory. I mean, similar to HAWK, it's an particle detector array. Utilizing the atmosphere as part of a detector and measuring the cosmic ray and gamma rays from the air showers. So LASSO is located in China, on top of the Tibetan Plateau at the altitude of 4,400 meters above sea level. And even, I mean, although it's such high altitude, but the transportation to the site is actually pretty convenient. I mean, there's a airport only 15 minutes away from the LASSO site. I think it's still the highest commercial airport in the world, which is actually at the same altitude as LASSO, and it only takes like 14 minutes or so to fly into Chengdu, which is a big city, major city in the Western China. And also less than an hour drive from the LASSO side, we have a base camp of our experiment in the city of Daocheng. And we have oxygenized dorms and meeting rooms and labs for the scientists. Okay, so the collaboration currently consists of more than 300 scientists and postdoc students from more than 30 institutions. Well, most of our institutions are from China, but also a few institutions from other countries also interested in the project. So, I mean, there are a variety of science topics LASSO can do. I mean, this similar topic actually has been reviewed. I mean, earlier this session by the previous speakers. But one of the most interesting topics is origin of cosmic rays. So since LASSO covering the energy range of the cosmic rays, both below and beyond the knee, and also the gamma rays, the corresponding gamma rays produced through these cosmic ray interactions. So it's a perfect detector to provide some unambiguous evidence of cosmic acceleration and propagation and look for the origin of galactic cosmic rays. And also in the context of multi-messenger astronomy, since LASSO has wide field of view and high duty cycle, as provide some unique information, some crucial information in this picture. So LASSO is actually a hybrid detector utilizing several different techniques. At the center of the detector is a so-called water Cherenkov detector array, with actually a three big pond with 300, approximately 300 by 300 meters with a 5 meter deep of water. So we have a large PMTs, 80-inch PMT and 20-inch PMTs to detect the chunk of light that produced by the air shower particles in the water. And the WCDA covering 80,000 meters square with 100% coverage, and is sensitive to gamma rays from about 100 GeV to tens of TeV. So if we want to detect higher energy particles, we need a larger array. This is what KM2A does. This kilometer square array covering more than 1 square kilometer in the area, and we have more than 5,000 scintillators to detect any charged particle that going through our detector. And we also have very important muon detectors, as Rasmus mentioned, covering about 4% of the ground. They are buried under 2.5 meter of dirt to, filter out the EM particles and only to detect the muon signal. So this is crucial for the gamma hadron separation of LASSO. Right, so apart from, besides WC and the KM2A, we also have 18 wide field of view Cherenkov telescopes. So these are telescopes pointing to fixed locations in the sky and mostly for measuring the cosmic ray spectrum. Right, so utilizing different techniques, LASSO covers a wide range of energy range, actually more than 4 decades from around 100 GeV to beyond 1 PeV using this WC and KM2A techniques. Right, so I just give one example of the one of the earliest, one of the first PeV gamma events detected by LASSO, and using actually a partial array called the LASSO array by the time. So you can see that in this event, the footprint of the shower triggers but only a few muon tags, so indicating this is a very gamma ray like shower. And you can see also we have signals from WCDA, even it's far from the core, but still actually trigger most of the detectors cells in WCDA. And fortunately, also falls in the field of view of one of the WFCTA, so you can see this helps the code reconstruction and also the energy reconstruction. So utilizing these different techniques, we can reconstruct pretty precisely the direction, the energy of an air shower. All right, so that event was measured by like a quarter of LASSO array, which was in operation since 2019, and since 2021 August, the full LASSO has been in operational. Right, so in this talk, I will highlight two of the recent results from LASSO. The first is the interesting region, the Cygnus cocoon region. So it has been postulated as the Pavotron candidate for a long time. So this star forming region, this OB2 association in this region has been postulated as the cosmic particle accelerator. And in the gamma ray energy range from Fermi-LAT, see a GeV emission, especially coincident with this region, and also the gas distribution, indicating the hadronic origin of the gamma ray emission. And at TeV energy range, Hawk and Argo also see gamma emission with a similar size. And now with LASSO observation, I mean, we not only extend the emission to the highest energy, but also we found that the angular extent is actually much larger. So it seems like previously we see only like a tip of iceberg. Now with a more sensitive detector, the angular extension is actually more than 10 degrees in this region. So to the left below, you can see the distribution of the high energy photons, about 400 TeV. And there are 8 of these photons have energy beyond 1 PeV. And the highest one is 2.5 PeV. This is the highest energy photon, gamma photon we ever detected from the universe. And from the table, you can see the for each photon, is the number of electromagnetic hits we detected and the number of muon hits we checked. So we can use a pretty straightforward gamma hadron separator, which is the number of muons divided by the number of electrons, and to give a good gamma hadron separation. And the possible contamination from these 8 photons is less than 1 from, hadronic cosmic rays. So we are seeing this ultra high energy gamma ray bubble with extension up to beyond 10 degree. And we try to correlate the spatial distribution with the CO and the 21 centimeter survey. So from the top panel at different energy bands, we compare the gamma ray morphology with the CO survey. You can see some nice correlation of these hotspots. So if we subtract those hotspots, and the lower panel is a comparison with the remaining emission with the 21 centimeter survey from the atomic hydrogen, you can see also some hint of a correlation. So this correlation indicates that the gamma emission is actually from hadronic origin. And the spectrum, if we only look at the central part, about around 2 degree Gaussian, which is consistent with the Fermi and Hoxes, the red flux points, the spectrum is consistent with what Fermi sees. But if you include all the entire bubble, which is the black line and points, we see the cosmic ray flux is actually much larger in this region. So I think the scenario we are looking at here in this region is a cosmic ray bubble with a super pervatron. So in the center, we have the OB2 region. Signals OB2 is likely a super pervatron. Although we don't know exactly the acceleration mechanism and the environment, but one thing we sure is it is a super pervatron with greater than 20 PeV cosmic ray accelerated, and these particles escaped and contribute significantly to the cosmic ray flux in the surrounding interstellar medium. So once they run into a molecular cloud, we see those clumpy distribution in the LASSO collaboration. So in the LASSO observation. So we have from this result, we have more or less good understanding of the propagation of the cosmic rays in this region, but about the acceleration, we need to do some further study in order to some numerical simulation in try to explain how such high energy particles are accelerated. Right. So the second result I want to emphasize from the both GRB almost 2 years ago. So LASSO with a wide field of view, we are not pointing telescope, so we just have to wait and the GRB to happen in right place in the sky and at right time. And LASSO was lucky. This both GRB happens at about 30 degrees from zenith angle, and we see the highest statistic from the ground-based gamma instruments, more than 60,000 photons above 100 GeV. So with such rich statistics, we can look at the light curves. If we compare the TeV light curves, which is the bottom left plot, to the MEV emission from the top, the TeV generally shows a very smooth temporal profile, suggesting it is a afterglow of the GRB, while the MEV is probably dominated by the prompt emission. And this is the first time detection from the ground of the onset of the GeV afterglow, which can provide very important information about the environment of the progenitor star. So one of the first papers we published with on this GRB is the decay part. We see a jet break at the earliest time, around 600 after the trigger. So the jet break is basically produced by, as the Lorentz factor decreases with time, we see a larger and larger surface area of the jet. And once our field of view is larger enough to see the entire jet surface, and then the decay of the light curve become steeper. So this is a clear change of the decay index, reviewing the open angle of the jet, which is actually less than 1 degree, pretty narrow. So this also explains why this GRB is so bright. We are just very lucky that such a narrow jet is pointing to the Earth and seen by LASO and other experiments. Okay, so of course, from the rich data of this GRB, there's a lot of other analysis we can do. The second paper we published is on the highest energy photons. Not only with WCDA, we also seen this GRB by KM2A with more than 100 photons. The light curve, well, is quite similar to that of WCDA, but KM2A provides some important information about the high energy. You can see to the right plot, the spectrum actually doesn't follow precisely the models, which indicates some interesting modeling of this emission mechanisms. And also the highest energy, 13 TeV, provides some strong constraint on the Lorentz invariance violation and on the actual background light. And more analysis are still undergoing to discussing about the fast rising part of the light curve and also any association with the prompt emission of the GRB. Okay, so I don't think I have time to go through a more detailed analysis of other sources, but I just want to mention that the first LASO catalog was published earlier this year. Among the 90 sources discovered by LASO, about 1/3 are new TeV sources, and about half of these 90 sources are ultra high energy sources above 100 TeV. So these are perfect targets for Pavotron candidates. And about 2/3 of these sources are extended. So we're not only analyzing, learn about the acceleration cosmic ray, but we also learn about the propagation. So the analysis on the individual sources are undergoing, and several papers been published on Pavotrons and pulsar nebulous / pulsar halo, but still a lot of unidentified sources are needed for the multi-wavelength analysis. And the diffuse emission paper has been published recently, and in the galaxy and other galaxy, we see gamma ray flux 2-3 times higher than the expectations from the local cosmic ray flux, which triggered interesting analysis, interesting discussions too. So LASO is not only an gamma ray detector, and cosmic rays most times we talk about as background, but cosmic ray itself are also important topic. So we recently published a paper on the all particle spectrum around the near region and the mean log mass. So last but not least, the time domain astronomy. LASO with wide field of view and high duty cycle is a perfect detector for follow-up observations, following up the GRB and neutrino alerts. And I can also do a self-triggered transient search, monitoring the whole sky half the sky at any time. And we are also keep continuously monitoring the known sources like AGNs and such sources, and send alerts to the community if we find a flare also. And finally, and there are also some analysis ongoing about pulses and binaries that could be also in time domain. All right, so come to a summary. So LASSO has been fully operational since 2021, and it opens a new window of ultra-high energy gamma ray astronomy by reviewing the first cosmic source above 10 PeV, with also several other discoveries on possibly nebula and supernovae, and it also has a great potential on time domain and multi-messenger astronomy. So please stay tuned for more results from LASSO, and thank you for listening.
Thanks a lot, Hao, especially for highlighting so clearly some key results of LASSO that really show the potential of these observatories. We have time for a quick question. Susumu?
Yeah, hi, Hao. So tomorrow I'm going to talk about the boat GRB, and while the data was very nice, and there's a rich multi-wavelength data set, I'll show that the models are still very much under constraint, and especially during the time of the LASSO observations, LASSO data itself was very exquisite, but there's very limited simultaneous data at other wavelengths, right? It's just GV from Fermi and just a little bit of X-ray data. There's no optical or radio. So you can't go back to the boat GRB, but now you have, for example, Einstein probe, and I believe you also have this SWAM GWAC telescope, the optical wide field optical telescope. How much are you collaborating with them to obtain these simultaneous observations of short time scale transients?
Yeah, that's a very high Susumu. Yeah, it's a very important, interesting point. Yeah, with so this boat GRB, as you said, with limited observation from other wavelengths, some people give us some challenge on the analysis, especially at the beginning of the on-site part of the light curve. So the Einstein probe and SWARM, yes, we do have a lot of we do have a program already ongoing. So I don't have detail, on top of my head, but either to some follow-up studies and also like a quick follow-up in time. But the advantage of LASSO is the data is just there, so we can always go back to our data even after the fact. So so yeah, that's an advantage we can do when collaborating those satellites and other wavelengths.
Yeah. Okay. Thank you very much.
There are a few other questions, but I think we are really tight on time, so maybe we can save for other moments of the meeting. Otherwise, I guess we get too late into lunch. So thank you very much again. And now we are going to listen from Petra Huntemeier from Michigan Tech about the SWJO project. Please, Petra. Thank you.
Hello, everyone. Can you hear me? Hello?
Yes, we can hear you, Petra.
While I'm setting up, may I ask one question to Hao? I wonder what's the status of GRB searches, untriggered GRB searches and things like that with LASSO? I just was wondering, is there any follow-up? Is there more than this event? Or if not, what are the limits of your observations?
Yeah, there's like a GRB follow-up program. I mean, they're both like after each GRB trigger for other GRBs, we search for emission in different time scale. And also in our data, we also have a program to look for transient events. And well, at this point, I can only say that we don't have a positive detection on any other GRBs, but the upper limits will be provided at some point.
All
I
right.
think that's
Yes.
also important for the SWGO development. I mean, since we want to know this information for our new experiments.
Yeah, that's also where my question came from. Thank you. All right. Last talk of the session. I try to be quick. Fortunately,
Not last. We have another one after. Jeez.
after lunch, right?
No, it's not.
Oh, okay.
So we have two
All right.
texts.
So
Yes.
I should even be quicker, but fortunately, you know, a lot of things have been mentioned already, so I can be rather quick regarding some of the background information that I will provide here. So you can see my slides, all right?
Yes.
Okay, so I will talk to you about SWGO, which we are planning to build in South America. Let's see. So you have heard before in this session about this in this very nice historical overview. There are essentially two techniques that we are using to detect gamma ray showers. One is the imaging atmospheric Cherenkov telescope technology, and the second is the particle detector array technology. Both are detecting extensive air showers. And while IACTs are measuring the progression of an air shower through the atmosphere, particle detector arrays detect a kind of a cross-section of that extensive air shower, as in its footprint in a particle detector array. And in particular, what has been shown in previous observatories is that one of the ways of doing PDAs is particularly efficient in detecting extensive air showers and also doing calorimetric measurements of these extensive air showers, and that's the water Cherenkov detector technology. And again, you heard a very nice introduction overview in the introduction. So these, what you see here is now a picture of ground-based gamma ray astronomy I call it in the teens, by which I mean in the 2010s. And so these are operating observatories across the globe during that time. And you see some of them are IACTs, some of them are PDAs, which are predominantly using different technologies, such as scintillation counters and gaseous counters. I will focus in the next few slides on the two experiments that you have heard about in the previous talks, and that is HAWK, which has been operational since 2015 in its complete configuration. And then 2019, LASO has been operating, but of course, as you just heard from Hao, with a partial array. All right, so let me say a few words. So you heard all these wonderful results already from LASO and HAWK. I just want to give a quick overview to give you an idea of really this wide field of view, where it came from and where it is now. And so for that, I wanted to start with Milagro, which was operated in New Mexico from 2000 to 2007. And over this entire time, Milagro did also do a galactic plane survey and found 8 sources for which the experiment gave a flux at a median energy of 20 TeV. So at the time, for a lot of the sources. We didn't have the observational power to do spectral measurements, but we were able to detect these sources. And the significance of this survey corresponds to 15 sigma observation of the Crab Nebula. So that was over 7-ish years that we got 15 sigma. And then in 2019, 2020, a HAWK came out with a catalog, and Alberto mentioned that, of 65 sources. Again, here the Crab Nebula was discovered at 190 sigma significance. And then we see the LASO catalog from 2022, and now I'm doubting my number here for the Crab Nebula, but LASO was able to detect 90 sources. Perhaps I need to check on my number for the Crab Nebula significance. Maybe Hao can correct me. So there's also an upcoming catalog from HAWK, which includes more data, 2,500 days of data. The Crab Nebula significance of this observation is 280 sigma. And stay tuned. In this catalog, HAWK is applying a different multi-source fitting approach than in previous publications. And we will hopefully have soon a paper published on this. All right, so great progress. Then you have heard of these mostly, so the discovery of TeV halos with HAWK, then briefly mentioned earlier, the discovery of ultra-energy gamma ray emission from jets of SS433. This source had been studied previously by IACTs, and they put upper limits on it, but at lower energies then HAWK detected it. HAWK saw the most significant emission in the tens TeV range, so above 20, 25 TeV. Since then has looked again and also could resolve in much greater detail the emission from these two jets that HAWK saw. And then on the right-hand side, and you have heard from Hao about this already, is number one with the partial array. In 2021, LASO published a catalog of 12 Pevatron candidates. And then also published ultra energy emission from, or peta-electron volt emission from the Crab Nebula. So you see great progress in wide field of view gamma ray astronomy that when I first started in the field, I didn't see it would be possible, but here we are. You heard also a lot about the boat, so I will not say much more about this and move to answer the question, how did this happen? And it mainly two things happened in comparison to previous experiments. We are going higher and we are going bigger. So on the left-hand side, you see a little bit, you see a picture of the number of electrons in an extensive air shower versus the altitude or depth in the atmosphere, depending on how you look at it. And you see here at 4 kilometers, slightly above you, this is the altitude of HAWK. And then to the left here toward almost 5,000 meters, not quite, we want to build SWGO. And then you see how you become in particular more sensitive to medium and low energy gamma rays. And then to the right here, I try to give you an idea of the comparison between the sizes of the different observatories. So this here is LASO. This is the KM2A in blue, and then in red is at the center of the array, the WCDA. And the WCDA approximately is the size of HAWK, by which I mean HAWK, the main array. And then the outrigger array is approximately that size. And then Milagro again here is approximately the size with its outriggers at the time of the core array of HAWK, albeit of course Milagro was at about 2,600 meters, while Hawk is at 4,100 meters. So, there are three main features. I always like to show this, and again, this has been touched upon already, but in the previous talks, there are three main features for wide field of view instruments using WCDs. That is the high duty cycle, and you have heard during the pandemic from Alberto that we did very well in terms of uptime with Hawk at 98%, and approximately 95, above 95 is something that should be easily achievable. Then the wide field of view, again, you had heard from Alberto about this. What you see here to the right is in particular an illustration of the wide field of view. And what I want to draw your attention to here is that, while the sky coverages for IACTs are very similar between IACTs and SW and wide field of view instruments, the difference lies a little bit in the instantaneous sky coverage, which of course for instruments like LASO or Hawk, and hopefully in the future for SWGO, is much larger. So then also, maybe I should say a few words here too. What's nice about this is here you see an overlay of Hawk field of view and SWGO field of view. And I should also say, it was mentioned earlier, this is the field of view when you assume 45 degrees opening angle. But of course, in principle, you see the whole sky. It depends on how ambitious you are with your analysis approaches, and you can go down to 60-degree zenith angle if you want to. Of course, then you run into issues with analysis of the data, but it's not impossible. And in fact, we have seen sources with Hawk in particular, for example, the Galactic Center, which is beyond the 45-degree zenith opening angle. All right, and then of course we have the good sensitivity and angular resolution and energy resolution above 10 TeV, which is illustrated here in this picture, in this plot from the paper that Alberto mentioned earlier, in which we verify the performance of the latest reconstruction pass of Hawk data, where we compare the sensitivity with other instruments. And it's interesting to see here, this is the 10-year sensitivity of Hawk, and it is interesting to see here where it intersects with the various instruments. So now if you compare it to 50 hours of observation times between Veritas, MAGIC, and HESS, you see that actually now we see the intersection of the sensitivity well below 10 TeV. And then here's also the intersection point with the northern CTA array, expected sensitivity for 50 hours. Of course, 10 years is a long time, to be fair, but also 50 hours of observation time is a long time for IACTs. All right, so this you have seen before. I just may want to add to what Alberto said. Indeed, this was a nice collaboration between HESS and Hawk. And what they did is they looked at this section of the sky in particular, where Hawk found 7 sources that hadn't been seen previously by IACTs. And of these 7 sources, HESS was able, after modifying their analysis to mimic what Hawk angular resolution and analysis do, they were able to recover 4 of these sources that previously were undetected, and the other 3 were simply below the sensitivity that you would expect to, with which you would be expect to be able to detect Hawk sources. So clearly there is a lot to be learned from the complementarity with the 2 instruments. And this is a plot you may have seen in previous SWGO presentations, which kind of illustrates that point. So here you see the time scale of observations and then the distance of objects you might be looking at. And the point that I was making earlier is this thing in terms of galactic extended sources, where an instrument like SWGO, a wide field instrument, can actually provide information to somewhat a smaller field of view instruments, even though, of course, CTA will have a wider field of view, so that deeper observations can be started with IACTs. And other cases of complementarity, of course, is looking at extragalactic sources, active galaxies, where you could, if for example SWGO detects a flare, the CTA instrument or other IACTs could follow up. And then finally, of course, transients, as you have seen in Hao's talk, is potentially a big deal. Although, of course, we need to admit that the boat is the boat, which means it's rather unique. But as Alberto pointed out, you never know what you see if you don't look. What does the community think about SWGO? So I don't want to go into detail with all of these quotes from the Astro 2020 Decadal Survey or the SNOMAS 2021 report, but just leave you with the fact that the panel on particle astrophysics and gravitation recommended that the US contributes about 1/3 of the cost of the instrument that will be SWGO at the level of around $20 million. The other thing I wanted to point out also is the importance of overlap with other instruments. And again, this is a little bit of a US-centric view because these instruments that you see here are NSF funded or have received some other US funding, significant US funding. But the point here is, of course, also in terms of science, you want to overlap with other funded instruments, as became clear in the question earlier about the boat. You really want to look at something that is transient at different wavelengths and with different messengers. And so that's shown here. So we have an expectation for nanograph to come online. We have we will see an improved and advanced LIGO in the entering the 2030s. And then, of course, there's IceCube Gen 2. So it just makes sense to also get new gamma ray instruments online with CTA, which is in now better shape and will soon start operating, and then SWGO, which hopefully we will get the money for, because again, as I mentioned earlier, it is providing information about phase spaces that are otherwise maybe not easily accessible. All right, so what is SWGO? SWGO, not surprisingly, will be building on the success and experience of HAWK and LASSO. And what we did at the time when we started out doing SWGO research and development was we looked in particular at two different approaches, a natural lake or an artificial pond, so a lake approach and a tank approach, where you build tanks out of plastic or steel. So who is doing this? There is now a global collaboration. So it's really nice and interesting to see because Milagro, for example, was a US project, then HAWK was a US and Mexico project, and then also had later on participation from Europe in it and China. And then LASSO is a predominantly Chinese project, but SWGO is a combination of all of the above. So we have 15 member countries now and supporting scientists from different countries. And the member countries do include the US, Germany, United States, but as you see, many other countries as well. The project is growing relatively fast, I'd say. So there are 41 institutions, were 41 institutions in 2019, and now we are approaching about 90 institutions, and we now have 15 countries. So people, also in terms of not only nice reports that were written about SWGO, people are also gravitating toward SWGO because it's interesting stuff that we may be able to see with it if we get funded. We also, of course, have an R&D phase plan. These are the milestones that we have that we want to reach over the course of the project of the R&D phase. 5 of them had been reached by the end of 2023. And I'm going to talk about these 2 here, the performance of candidate configuration and the preferred site identified. And you may already guess it, these have been accomplished in 2024. So for the first one, M6, where we look at the different configurations and detector designs, we looked at 6 different designs, and they are signified. They are essentially 3 groups. They are a group of designs which have a double layer approach, in which we have a larger volume on top and a somewhat smaller volume in the bottom, which should help with muon identification. And you have heard this before. This is extremely important for gamma hadron separation. And then we tested different photomultiplier tubes simulated, and also different dimensions. So there's kind of a large design which approaches Hawk dimensions, and somewhat smaller designs, and some of these have different PMTs in terms of their size, large area PMTs or other approaches. Then we have a somewhat novel design with a plastic tank and 3 PMTs viewing the water volume. And then this here is something which we often called the Hawk design or Hawk-like design, although Hawk is much bigger. The detector unit in Hawk is much bigger, and the water volume is viewed by 4 photomultipliers. And then we also used this first design, this one of the double layer design, the smallest of it, to arrange tanks in different configurations. Again, for comparison, here is the Hawk and LASSO dimensions, and tested essentially what the sensitivity is. And what these designs signify is some have 2 zones of arrays, some have 3 zones of arrays. The extent, of course, the diameter or the radius is different, and then also the fill factor. So testing these, we looked at different science cases. Again, I don't want to take too much time on it, but again, we looked at typical performance parameters such as angular resolution and gamma hadron separation, but then we also, through instrument response functions, looked at how different science cases would behave or would be studied. And what we then found from this is that the double layer design, perhaps not surprisingly, because of its muon layer, performs the best, and that the detector unit performs the best, probably because it has the deepest water volume. But we only tested, like I said, like from a smaller volume to a larger volume, and now we want to kind of scope this out a little bit more and see if in between these dimensions, which one can we optimize the dimensions a little bit further. And then of the configurations, the so-called A4 configuration with an 80% fill factor in the zone 1, 4% zone 2, and 1.26%, 5% in zone 3 performed the best. And this is also then the sensitivity curve, which I'm showing here. That's based on this A4 design. And you see, again, this is compared with a LASSO 1-year performance. This is a 1-year performance from A4F4, and the CTA 50-hour performance, south. And again, interestingly, you see kind of this intersection at around 10 TeV. Now, of course, all of this is very approximate, but I find it remarkable that we always end up around 10 TeV with our intersection in terms of sensitivity to DC sources. And then to the right here, and I should mention that it's not only a matter of detecting sources, right, with this sensitivity. It is also important to have a somewhat acceptable angular resolution in order to really do associations and do combined science analysis with CTA as well, for example. So this is what's shown here. Again, there's a bit of a range of angular resolution for SWGO for the inner array. But we are a lot more ambitious compared to LASO or HAWK, and we are trying to approach CTA angular resolution. This is really, I think, often not talked about, but it's extremely important to do that, in particular, of course, in the Southern Hemisphere. Site, we looked at 3 countries, and in each country, in Peru, we looked at 3 sites. We looked at 2 sites in Chile and 2 sites in Argentina. The sites are located between 13 degrees south and 24 degrees south. We did a site visit in the fall of 2022, which was interesting because it was barely when these countries, so to speak, reopened for travel. And we looked at 3 sites in Peru, then followed by visits in Chile, and then followed by a visit in Argentina. This is the group of people we, for example, met with in Peru, and some of our colleagues at the different sites. This here is Chile, then some sites here in Peru and Argentina. Now, the sites that we looked at had different elevations, and also, so number 1, we looked at a relatively low site in Argentina, it's called Alto Tucumar, still higher though than LASO, and the highest site is in Peru, Yankee. And the other thing you should pay attention to is, of course, the spread here. So we looked at very extremely flat sites, Imata in Peru, to somewhat, you know, steep sites in Chile or Argentina here. We produced a site report from these visits, summarizing strengths and weaknesses, making recommendations to the different site candidate hosts in terms of what do we want to know, and what is the information we think is important. And that then led to a new request for information to all the site candidates. All the while, we were trying to take into account responsible siting, which is, I think, extremely important. And perhaps in particular, the US colleagues are very sensitive to this, given the situation in Hawaii. You want to make sure that that the people living nearby the site are comfortable with you being there and buy into your project and embrace the project, which is an important aspect in our site evaluation. So perhaps a new reveal, although maybe some of you already visited the SWGO website, we decided where we want to go. We decided to go to a site called Pampa La Bola in Chile, which is located here. So it's one of the southernmost sites. It will be exciting now, because now we will have to start our negotiations with our Chilean partners to build SWGO there. We also, of course, want to be sure that we cover all our bases. So we have identified a backup site as well, which is this very flat site in Peru. And stay tuned for more news regarding this. It's getting serious now. So just as to summarize, as you see, SWGO is a very young collaboration. So we were just really founded 5 years ago, and that was before the pandemic. So despite the pandemic, we made major strides in realizing SWGO. SWGO will be an international multi-agency project, which is a little bit of a different approach than for HAWK and LASO. So we truly see everyone as a level-eyed partner, and it's not just like a US project or a European project or an Asian project. It's really, and South American, obviously, it's really a project from all these different continents, which is reflected in the spokesperson team. So if you have questions, for example, about this talk or about SWGO, you can go and talk to Ulysses, who is there after this session. So we have spokespeople from Europe with Jim Hinton, South America with Ulysses, and then North America is myself. We also have a steering committee, which consists of representatives of the 15 member countries. And actually, it, I think, speaks to the strength of the collaboration that we were able to coalesce around a primary and backup site rather quickly. And SWGO will be, I think one cannot emphasize this enough, will be the first of its kind in the southern hemisphere. And it will survey large swaths of the southern hemisphere sky with unprecedented sensitivity and novel detector technologies. All right, well, thanks for your attention, and I take questions now.
Thank you very much, Petra. In the interest of time, I think I can take questions about SWGO. But thank you very much for your great presentation. And the next speaker kindly agreed to speak after lunch. And since we had a cancellation in the afternoon, everything will fit well. So we can go for lunch and come back at this time. Thank you very much. Thank you, Petra. Thank you all the speakers of the session. So, okay, welcome for the second session. That's the day. And Marcus, I give the floor to you.
Hello, welcome everybody. I'm Marcus Betia from Northwest University. Sharing this, our first speaker will be online. Actually, the first three speakers will be online. Just give me a second here. So first speaker is left over from the last session that ran over time a little bit. So Todomasa Kabata will talk about the Tibet air shower array. Please.
Hello, can you hear me? Hi.
Yeah, hello. We're just waiting for your slides to come. Oh, okay. So sorry, I misunderstood that. Yes, correct. We see your slides now.
Can you see my slide?
Yeah, yes, we do.
Or can I start my talk?
Please do.
Okay, so today I'm going to talk about a recent result from the Tibet air shower experiment. Okay, this is a joint experiment between China and Japan. Okay, so let me start with the introduction of our experiment. The Tibet air shower array is located in Tibet at the 4,300 meters above sea level. The array consists of about 600 scintillation detectors and covering about 65,000 square meters in total. As you know, the primary gamma ray or cosmic ray interact with the atmosphere and produce many secondary particles, mainly positron and electrons. And each scintillation detector recorded a timing and particle density of these secondary particles. And so the air shower direction and energy reconstructed from their information. The angular resolution is about 0.2 degree, and the energy resolution is estimated to be less than 20% higher than the 100 TeV gamma ray. Okay, so left figure shows the typical event example of the detected gamma ray candidate. The circle size each point represents the particle density for each detector, and the color scale indicate a relative timing. The primary gamma ray energy reconstructed from the lateral particle density distribution here. We refer the S50 parameters, which is a particle density at the distance of the 50 meter from the air shower axis. In this case, reconstructed energy estimated to be 250 TeV. Okay, next, let's move on the underground water Cherenkov muon detectors to discriminate between gamma ray signal and cosmic ray background. We have a total 3,400 square meter water pools under the existing air shower array. This figure shows the side view of one unit. Each unit size is 54 square meter in area and 1.5 water depth. And each unit has one down-facing 20-inch diameter photomultiplier tube, and inside walls and floors are covered by a white Tyvek sheet to reflect Cherenkov light produced in the water by muons. And the muons in an air shower penetrate into the underground, but the electromagnetic component absorbed by the 2.4 meter soil over bottom here. So such a deep underground detectors enable us to discriminate muon component and separate gamma ray signal from the cosmic ray background, as shown in the next slide. Okay, so these two plots demonstrate the number of muons as a function of the air shower size. Left is a gamma ray Monte Carlo result, and right cosmic ray data. The non-muon events are plotted here, and these events dominated in the gamma ray induced air showers. On the other hand, cosmic ray induced air shower have much more muon like this. And black solid lines in each panel indicate optimize the muon cut line to maximize the gamma ray signal to noise ratio. And then at the 100 TeV energy region, we have succeeded in rejecting cosmic ray in 99.9%, while 90% gamma ray keep after the muon cut. Okay, so here I will show you the first result for the brightest TeV source, Club Nebula. The rest two plot show the gamma ray image in the direction of the Club Nebula above 10 TeV and 100 TeV energy region. The maximum energy was reached to 450 TeV at that time, and this was the first report of the sub-PV gamma ray from the astrophysical source in 2019. The other detected sources in 100 TeV energy region are listed here, which we will discuss later briefly. Okay, so next let's move on the diffuse gamma ray analysis. This plot shows the gamma ray-like event distribution after the tight muon cut in the equatorial coordinate. Blue point gamma ray-like event in 3 different energy range, 100 TeV to 160 TeV and 160 to 400 TeV and above 400 TeV. You can see some event concentration along the galactic plane. In the highest energy beam, dozen of the event clearly is seen along the galactic plane with almost background free. As shown here, galactic latitude profile. A red point shows the experimental data across our field of view, including a source contribution. As you can see, the clear peak is seen in each energy range with a high statistical significance. A gray shaded histogram are estimated from diffuse gamma ray model developed by Lipari and Barnett, assuming the hadronic scenario. Okay, so in this slide, the energy spectrum of the diffuse gamma ray. Upper panel shows the diffuse energy spectrum in the region closer to the galactic center. Target region is completely same as the previous observation by Algo YBJ, as shown by a blue point in TeV energy range. And the red point shows our measured fluxes after the excluding source contribution from the non-TeV sources within a 0.5 degree radius circle listed in the TeV catalog. Then these measured fluxes are compared with the diffuse gamma ray model by Lipari and Barnett, assuming 2 different hypotheses here, as shown by solid curve and dashed curve. One is that the cosmic ray spectrum is identical in whole galaxies, solid curve. The other model is that harder cosmic ray spectrum getting closer to the galactic center dashed curve. The lower panel shows the including anti-galactic center region, whereas searched by Casimir observation for more than 20 years ago here. And our measured flux is a reasonable agreement with the both diffuse models calculated by Lipari and Barnett, assuming the hadronic cosmic ray origin. Okay, so here I will show you the recent Russell diffuse gamma ray result compared with the Tibet. The Russell spectrum, as shown by red point, is a few times lower than the Tibet, but it cannot directly compare due to the large masked region near the galactic plane, like this by Russell. So the Russell might underestimate the diffuse gamma ray flux, or our measured flux by Tibet includes some source contribution. So to check this, we compare our diffuse gamma ray signals with the first Russell sub-PV source catalog. Red point shows the Tibet diffuse event, and blue circle shows the Russell sources. And surprisingly, the Tibet galactic diffuse gamma ray event do not coincide with the Russell sources, except Cygnus-Cocoon extended region. Okay, so anyway, IceCube very recently reported on the galactic diffuse neutrino published in the science paper. In this paper, they mentioned that IceCube neutrino flux smoothly connect to the neutrino flux estimated from the Tibet sub-PV diffuse gamma ray result, as shown by black points. This factor suggests that these Tibet diffuse gamma ray originate from the cosmic ray hadronic interactions. Okay, so finally, let's move on to some Pevatron candidate observed by Tibet. First one is a very famous Pevatron candidate, SNRJ G106. The energy spectrum extends beyond the 100 TeV energy region, and color map shows the gamma ray excess here, which is associated with the shell type SNR. But this is slightly shifted from the gamma ray pulsar, as shown by a yellow point. And our excess is well coincident with the molecular cloud measured by 12CO survey Xi'an contours. So it's a very good candidate of the Pevatron. So proton maximum energy about 500 TeV, and proton total energy 10 to 49 ergs, assuming the hadronic scenarios. Okay, so the second candidate, HJ 1843, this situation is very similar to the G106 in previous one. Gamma ray excess position is consistent with the both SNR and pulsar, and the spectrum smoothly connected to the TeV energy region and extend up to the 100 TeV energy region. And the extended gamma ray excess coincide with the ambient molecular cloud, and the proton cutoff energy also 500 TeV, and proton total energy 10 to 49 ergs. Okay, so one more Pevatron candidate, HJ 1849, which is middle age pulsar in the nebula. We published paper recently. Gamma ray excess position consistent with Russell observation, blue point, and coincide with 12CO molecular gas as shown by green contours.
Could you please, you're out of time, could you please speak?
Okay, so this is energy spectrum looks very flat spectrum. And if we assume the hadronic model, proton cutoff energy reach the PV energy region. Okay, so let me summarize my talk. We have successfully observed the sub-PV point source and diffuse gamma ray for the first time and detected the sub-pivotal candidate. We have opened a new energy window in the gamma ray astronomy. However, currently there is no sub-PV instrument with enough sensitivity in the southern hemisphere. Next step goes south. Some projects are ongoing and planned, such as Alpaca, Mega Alpaca SWGO, CT, and the next generation neutrino experiment. Okay, this is conclusion of my talk. I stop here. Thank you for your attention.
Yeah. Thank you very much. We have time for 1 or 2 questions, please.
Thank you very much. Thank you very much. May I ask you please show the slide number 7?
This one?
Yes, yes. I think I have a question concerning this events which are above 100 TeV, where you measure 24 gamma ray candidates against 5.5 cosmic ray background events.
Yes.
I remember in the publication your argument about cosmic rays is linked to energy resolution. You claim that because your energy resolution is 20%,
yes,
then I think you can easily define your background. But I think reality is more complex in my understanding. So energy resolution deals with just maybe part of your events, 34% or 64%. But if there is migration of events on lower level, let's say on 30% level, 25% level, your energy resolution is not going to help you.
No.
So,
I checked
yes.
energy
I think
migration.
let me ask you the question. Huh? Let me finalize my question. Do you have the migration matrix of your events? I think without migration matrix, it's difficult to answer this question. So energy resolution is of no help, I think.
Yes, I checked.
There should be a migration matrix, and then
migration matrix. Yes, of course, we consider the energy resolution in our Monte Carlo simulation, and we check the migration from lower energy to above 100 TeV energy region. So our migration less than 10% to the higher energy region.
So you do consider migration matrix, you mean, but it is not in the paper. It's not in the paper.
I quote that in the paper. You can check.
Yeah, maybe we can discuss this offline because I think we need to move on. So let's thank Cosmas again.
Thank you very much.
The next talk is an invited talk, then online by Ruji Yang on laser observations of massive stellar clusters. Ruji, if you're ready, please share your screen.
Yes, I'm trying to share my screen. Can you hear me, by the way?
Yes, we hear you.
Okay. Okay. So can you see the screen?
Yes, we do.
Okay. Okay. Good afternoon, everyone. First of all, I want to thank the organizer to give me this opportunity to present some recent last results, especially on the specific topic of young massive clusters. And this is the outline of my talk. Firstly, I will briefly introduce the motivation of the camera observations on young massive star clusters. And then I will talk about this recent results, mostly from the observational point of view, both with before LASSO and with LASSO. So the motivation comes from the origin of cosmic rays. I think in our galaxy, the supernova remnant are long believed as the best promising candidate of cosmic ray accelerators. And this idea is supported by gamma ray observations as well, especially in 2013. These Fermi collaborations, they have clearly detected the so-called pion bump spectral features below GeV. And this was regarded as a decisive proof that the supernova remnants do accelerate cosmic rays. But in this kind of observations, all the gamma ray spectrum for the mid-age supernova remnant all show a clear break or cutoff in their spectrum at about 10 GeV. So this means this kind of supernova remnant, although we know that they do accelerate hadronic cosmic rays, but they cannot account for all the cosmic rays up to the knee region to 1 PeV in our galaxy. And a natural idea is this mid-age supernova remnant. The shock speed of them deaccelerated is not high enough to accelerate particles to high enough energy, and for higher energy cosmic rays, they should be accelerated in younger systems, and indeed, all these historical young supernova remnant, they are quite bright in TeV energy range. But if we examine in detail of their TeV spectrum, we also found a clear cutoff break at about 10 TeV or even earlier. So this means the corresponding cosmic ray energy should have break or cutoff below 100 TeV, which is still one order of magnitude smaller than what we needed to explain the cosmic spectrum up to PeV. And also, this TeV observations has put quite stringent upper limit on the idea of the very young supernova remnants. These observations come from the Hess on the youngest supernova remnant, G1.9 plus 0.3 in our galaxy. This supernova remnant is quite unique. It has an age of only 100 years, and the shock speed is believed to be as high as 18,000 kilometers per second. But the Hess observations didn't detect any TeV emissions, and the upper limit set by Hess has shown that the total very high energy protons accelerated by this source in its first 100 years should less than 10 to 45 ERG, which is far less than expected if we want this kind of supernova remnant to account for all these PeV cosmic rays in our galaxy. And so someone may argue that there may be some alternative cosmic ray sources in our galaxy which can account for the cosmic rays in the highest energy. And one such kind of candidate is the young massive clusters. And in fact, from the observational point of view, there are some independent hints that this kind of systems, they do accelerate cosmic rays. For example, this cosmic ray distribution derived from the diffuse gamma ray emission, they have a same peak with these OB stars rather than with supernova remnants. And this isotope measurement of this iron-60 and neon-22 also favor a superbubble origin of cosmic rays. And from a theoretical point of view, these OB stars, they are powerful enough to accelerate cosmic rays. And this idea, in fact, was proposed by Szyszewski and Montemore as early as 1983. And if we account for all these wind powers of these OB stars in our galaxy, they are enough to accelerate to account for at least a significant portion of cosmic rays in our galaxy. And if this is true, we expect these gamma ray emissions due to the cosmic ray gas interaction near this kind of accelerators. And okay, this is the this figure shows the cosmic ray distribution in our galaxy derived from diffuse gamma rays, and this data points shows the distribution of cosmic rays, and the blue curve and the red curve shows the distribution of OB stars and supernova remnants respectively. So we find a similar peak of this cosmic ray distribution with OB stars rather than with supernova remnants. And also there are some other recent observational hints. One is this gamma ray emissions associated with this ionized gas, because we know most of the H2 gas, this ionized gas, they are related to the very young massive stars, even before their explosions. And in this diffuse gamma ray emissions, we recently found a quite hard component associated with this H2 gases. And you see this is the blue curve here shows the spectrum of the diffuse gamma ray component associated with the ionized gas, and this is significantly harder than this than the gamma ray spectrum associated with the total gas volume density, gas column density. And this hard spectrum also reveal the kind of accelerated spectrum rather than propagated spectrum. So, and this is recently further checked by some other groups. For example, this Giada and her colleagues, they found quite significant gamma ray emissions associated with the several famous H2 regions in this nearby Vela giant molecular clouds. And they argue that this is a hint that these regions are harbor cosmic ray accelerators. And these structures, in fact, are very young, and they are too young to have any supernova remnant event. And also they found some correlation with these H2 regions and unidentified gamma ray sources, especially in GeV band. This is quite significant. I think they put this paper on arXiv very recently, within this week. And also, if we look in detail in some famous H2 regions, we found this corresponding diffuse extended gamma ray emissions. So one example is this NGC 13603. And we know these H2 regions, they are linked to very famous young massive star clusters. And in these structures, we also found some hard spectrum gamma ray emissions and with extended spectral structures. So all these hints, they support the idea that these young massive clusters, they are responsible for at least some of the cosmic accelerations. And these structures, in fact, they are very compact, and they harbor dozens or more very powerful OB stars and Wolf Rayet. This is the distribution of young massive cluster in our galaxy. And but I want to argue that this list is far from complete, because all these structures, they lie in very dense and complex regions, and they suffer very strong extinction. And all the survey now is not complete. And from theoretic point of view, these young massive clusters, they can potentially accelerate cosmic rays. For example, in this Beekhoff 2014 paper, they argued that the colliding surface of stellar wind and the supernova remnant may be and supernova shock may be the best candidate to accelerate particles even beyond PeV. And from the gamma ray observational point of view, there are really quite a lot of gamma ray sources associated with this kind of systems. For example, the famous Cygnus cocoon and Westerlund 1, Westerlund 2. And we also have some recent detections in Fermilab, especially in Fermilab energy band. The most famous one, of course, is the Cygnus cocoon. And this extended gamma ray structures has been detected by Fermilab, as well as the Argo and Hawk. And this is a very, very striking structure. It's very bright and very extended. The physical size is up to more than 50 parsec. and the energy is HAWK has detected the emissions above 100 TeV from this source. This already means this cosmic ray energy should be above PeV. And another interesting site is the Galaxy Center. And the Hess in 2016 published their observations on the diffuse gamma ray emissions in Galaxy Center. And they argue that from the spatial morphology and the spectral features, they argue that this region should harbor PeV particle accelerators. One natural candidate, of course, is the supermassive black hole in the Galaxy Center, but I want to mention here that this region also harbor several very powerful young massive star clusters, and these star clusters are also possible accelerators to account for the diffuse gamma ray emissions in Galaxy Center region. And also another candidate is Western 1. This is also a very extended gamma ray structures. If we believe it's associated with the star cluster Western 1, then the physical size of these structures should be more than 100 parsec, and Hess recent detection reveal a spectrum up to 100 TeV. And another interesting thing for these structures is because most of them are extended, so this means we can, in principle, derive the cosmic ray distributions by a gamma ray profile as well as the gas distributions. And we did it for several bright ones, and we found nearly all of them obey a universal 1/r distribution of cosmic rays, and this means a continuous injection of cosmic rays from the central of these systems. And also, if we check in detail the spectral shape, we found all of these systems are very promising Pevatron candidate, because their spectrum is very hard and didn't show any hint of cutoff break in 10 TeV level. And so LASSO became the best instrument to study this kind of structures, because they are very extended and they do need this information from higher energy to identify whether they are Pevatrons or not. And LASSO is good at this task because it has the very good sensitivities above 10 TeV, as well as a very large field of view. And this can be very important for study of this kind of extended sources. This is an incomplete list of these young massive clusters in LASSO field of view. This list was made before this LASSO's observations, so we didn't know what can be done at that time. And also there are some hints from the first 12 sources detected by LASSO in the galactic plane. There are several regions. There are 4 sources in the first 12 ultra energy sources are potentially related to young massive star clusters.
3 minutes.
Okay, I'll be fast. Okay, sorry. And okay, I'll go directly to our results on signals. So of course, the most promising one and the best one for LASSO is signals. And we detected the 1.4 PeV photons from this region in our first 12 source papers. And after that, we have a detailed analysis for 2 years more exposure, and we found a very extended gamma ray structures in this region. Although the result depends heavily on the assumption of the galaxy diffuse emission, but even with this most conservative assumptions, we detect excess of gamma ray emissions up to at least 6 degrees on top of the diffuse gamma ray emission. And this means a physical size of at least 150 parsec. And in these detections, we didn't find clear energy dependence both on the position and the extension. So we believe that this kind of feature, they favor a hadronic origin. Also, with likelihood analysis, we resolve this very complex region into mainly 4 components. One is this inner bubble. This is similar to the so-called Fermi cocoon, formerly detected by Fermilab and Hawk and Argo. But on top of that, we found some more extended structures, which is we call it Fermi bubble, and this has an is in general spectral correlated with H1 gas and has an extension of more than 150 parsec. I think this is also mentioned by Hao in this morning's talk. And as well, we also have hotspots associated with the molecular gas, and these hotspots, they also show harder spectrum, which may hint for some kind of cosmic ray propagation effects. And we also have a very bright central source, in addition to this known Poisson nebula and binaries. And from the gas distribution and the gamma rays, we can, in principle, derive the cosmic ray distributions. And we found that the cosmic ray density in this region is much higher. It's order of magnitude higher than the cosmic ray C density, up to several hundred parsec. This means this region, they do harbor cosmic ray accelerators. And this figure shows the distribution of the highest energy photons above 400 TeV. We detected more than 60 photons of the above 400 TeV. So by eye, we can see this very extended gamma ray bubble structures. And also, we found a clear concentration of the highest energy photons in this very center. This may hint for injection. And from the phenomenological point of view, we can fit the observed gamma ray spectrum and morphology in a very simple physical picture. That is, the central source inject cosmic rays up to several PeV, and they propagate into the nearby ISM, interact with the ambient molecular gas and atomic gas and produce these gamma rays. And they need the slow diffusion to explain the observed gamma ray emission. And this is also expected near the cosmic ray accelerator. And in addition to Cygnus, we also have the observation of the W43. This is a similar system in our galaxy. This region is very famous because it contributes 10% of our galactic star formation rate, and also harbor a very huge H2 region, these ionized gas regions. We also have detected that in G, and LASSO also detect this source in above in all its energy range from 1 TeV to nearly 400 TeV. But the spectral shape of this system show clear difference with Cygnus, because in Cygnus we didn't find any strong evidence of the cutoff or break, but in this source we see clear cutoff features, and we have a nice detection of the shape of cutoff in this system. So this may indicate some difference of this system with Cygnus region. So okay, I nearly finished. So I want to mention is all these systems, they are very complex, they are very crowded, and to identify the true nature of this system, the radiation, to pin down the radiation mechanism and the particle acceleration mechanism, we need something more than LASSO. We need a better angular solution. And to facilitate this, we have some idea to update LASSO, to build, we plan to build 32 Cherenkov telescopes in LASSO site. And this project is called LECT and is already fully funded. We will finish the construction of this Cherenkov telescope arrays within 2028. And from the red figure, you can see this array has a very good sensitivities, and also because this Cherenkov telescopes, it can reach an angular resolution of several arc-minute to do very good synergy with LASSO. And okay, this is my conclusion. Thanks.
Yeah. Time for one quick question. Yes.
Thank you very much for interesting talk. I have a question about the Cygnus region. So I think you say there are 66 photons, PeV energy photons, and just 7 are in a small group of half a degree. So roughly, I can say we are talking about maybe at least 10 sources or maybe more.
It means
assume
no.
that-
Why
No.
do you think it's 10 sources? This is we do not expect. This is 400 TeV photons. We do not expect it 400 TeV sources in this. Too many 400 TeV sources. I think, of course, this region harbor this very famous TeV source. This, for example, this pulsar J2032. But for that source, we detect a very clear spectral cutoff at several, I think, dozens of TeV. We do not expect this source they contribute significantly to 400 TeV sources, and I think this is also true for a lot of this non-TeV sources. This is 400 TeV.
Okay, 400 TeV. But what happens that this a large number of sources, I assume several photons are representing a single source maybe, that there is such a high clustering of sources in one location within 10 degrees. So do you have any clue or any idea or any discussion that you can bring to, that you can tell us?
Yeah, this is, yes. So we believe this most of this ultra high energy photons, they are from this unit from this extended gamma structure. We call it the Cygnus bubble, and this is because in this region we have a very strong injection of cosmic rays. So we do expect the concentration of cosmic ray density near the accelerators as well. So as consequently, we also expect this higher gamma ray flux in this energy range near this accelerator. So this means we just observe the injection of the highest energy cosmic rays in this region. I think this is our current understanding. Of course, there are potentially there are also can be some contribution from these sources, because this region is very interesting, very complex. For example, this is not only we not only have this star cluster here, we also have this microcrystal Cygnus X-ray here. So it's possible that some of this highest energy photons, they are also related to this microcrystal, but this needs to some further investigations.
Right, thank you very much. Let's thank Roger again.
Okay.
We have a second online invited talk by René Giacinti on particle acceleration at pulsar wind nebulae. René, when you're ready, would you please share your screen?
All right, thank you very much. So, share. Can you see my slides in full screen?
Yes, we do.
All right, perfect. So thank you very much for the invitation. And also sorry for not being able to come at the last minute due to an unforeseen technical issue. So my talk is about particle acceleration to very high energies in pulsar wind nebulae. So, and it's basically based on these works down there. So we now know for sure that pulsar wind nebulae are very amazing particle accelerators, and that they can accelerate electrons and positrons up to at least PV energies like in the Crab Nebula. So here you see the spectrum, which has now been completed up to PV energies by the LASSO Observatory. So we know for sure that the Crab Nebula is able to accelerate particles up to a few PeV at least. Now, how this works is remains relatively unclear. And I'm going to focus on the particle acceleration mechanisms that must be or may be at play in this source and in pulsar wind nebulae in general. So this is the synchrotron, what you also see in synchrotron. So here on the left-hand side, it's a composite image of the Crab Nebula, and on the right-hand side, it's the X-ray view of the Crab Nebula with a pulsar here with a dot in the center, and the termination shock surrounding the pulsar. The pulsar should be coinciding with this ring that you can see here and that I'm showing with the cursor of my mouse. So of course, the main suspect for the acceleration site and acceleration mechanism would be first order Fermi acceleration mechanism at this termination shock. At the termination shock of the relativistic pulsar wind. And it's known that if cosmic rays manage to be well scattered on both sides of such shocks, you would expect efficient particle acceleration with an e⁻².2 power law spectrum, as demonstrated in these seminal papers down there. However, in a simple, just to say things in a very simple way, we also know, unfortunately, that the geometry of the magnetic field in this region is not favorable for particle acceleration at such shocks. So in other words, such shocks cannot accelerate particles in principle. So this is just a simple sketch that I'm showing you here. So here the fluid is coming from the left-hand side, which is labeled, the region labeled upstream. And we know that the magnetic field in the shock region of pulsar winds should be toroidal. So close to the shock, it should look like this. So for example, perpendicular to the screen. So the fluid flow is going from the left to the right. And the shock surface is denoted by this vertical black line. So the fluid is ultra-relativistic in the striped wind on the left with a large Lorentz factor, in any case much larger than 1. And when you have a particle, electron or positron, incoming from that region, when it enters the downstream region, well, as you know, charged particles rotate around their magnetic field. And since the magnetic field is advected at a fraction of the speed of light in the downstream of the shock, this region on the right-hand side, the particle will basically follow a trajectory similar to this red line shown, to this red curve shown on the screen. So you can see that the particle actually never crosses or recrosses the shock after entering the downstream. So in other words, first-order Fermi mechanism cannot work. So of course, this is a very simplified view of what is actually going on in terms of particle acceleration, or more precisely, lack of acceleration at such shocks. But particle in cell simulations basically confirm this, both in the unmagnetized or magnetized case. Ultra-relativistic perpendicular shocks cannot accelerate particles to very high energies. They are either not able to accelerate to reach very high energies, or it's way too slow. So in other words, it does not work. And that's why a number of works have studied other possibilities for accelerating particles in pulsar wind nebulae. And in particular, there is a number of different variations related to the possibility of accelerating particles via magnetic reconnection. So for example, this work from Cironi and Spitkovsky in 2014, or this work on reconnection close to the shock, so reconnection in the striped pulsar wind, in this work from Lugo and Kilian in 2021. Whether magnetic reconnection is able to accelerate particles up to PeV energies in the Crab Nebula and in other pulsar wind nebulae still remains to be seen. So in our work, in our works that I'm going to explain in more detail now, we have investigated another possibility, which actually was not considered before, but could well solve the problem of particle acceleration at the shock. So basically, another possibility, so this possibility that we suggest is that actually taking into account the global magnetic field geometry in the shock region by taking a more realistic geometry for the magnetic field allows for efficient particle acceleration in one region of the termination shock of the striped pulsar wind, more precisely in a donut surrounding the intersection between the equatorial plane for rotation of the pulsar and the termination shock surface. All right, so this is a simple sketch. So this is a sketch of, so on the left-hand side, you can see basically the image of what the Crab Nebula looks like on the sky, with a black dot in the center being the Crab pulsar location, the red circle the red ellipse being basically the termination shock location, and the blue region is the X-ray nebula, which is the cooling zone of TV electrons that we assume to be accelerated at the termination shock. Now, in the middle panel, this is just an inset of 1/2 of the striped wind surrounding the pulsar. So the pulsar is again this black dot. And this region with an opening angle theta between the two green dashed lines is the interesting region of the striped winds, with the current sheet denoted with this zigzaggy sawtooth-like pattern in green. And the termination shock location is shown with this red curve. And the equatorial plane is this horizontal line in dashed blue. So the region where we actually where we actually see particle acceleration in our simulations is in this smaller region, which in 3D has a donut-shaped region around the equatorial plane region, intersection with the termination shock. So now if you zoom in, what you see in practice is that actually the global geometry of the magnetic field is the following. So the magnetic field, well, the phase average magnetic field is basically 0 along the equatorial plane. And we also see from MHD simulations like in the works of Oliver Port and colleagues a decade ago, the B field is very weak in this region in the downstream of the shock too. And the B field is basically perpendicular to the screen and pointing towards you, for example, above the equatorial plane and in the opposite direction below the plane, or vice versa, depending on the polarity of the pulsar. So basically what we do in our simulation, we assume this kind of simple geometry for the fluid flow, so ultra-relativistic fluid flow on the left-hand side in the upstream, and 1/3 of the speed of light in the downstream, or any other slightly greater fraction of the speed of light if B fields are dynamically important in the downstream. Then in terms of magnetic field strength and geometry, so for the geometry, we follow this geometry, and in terms of strength, we use, as motivated by MHD simulation results, we use this kind of profile where the B field basically is 0 on this equatorial plane at z = 0 here, and grows to a positive value, to a negative value along y above, and a positive value below for z negative, like this formula. And for the field in the upstream, so that was for the field in the downstream, but for the field in the upstream, we of course satisfy the jump conditions that we expect the field to follow. And on top of this, we add also a little bit of 3D turbulent magnetic fields on top of this. All right, then we inject particles, and we follow these test particles in these 3-dimensional simulations, and we integrate basically the trajectories of individual electrons and positrons in 3 dimensions. All right, so these are the results. So on the left-hand side, you see the results for the particles with the positive sign of charge, so positrons. Again, the vertical dashed line here is the termination shock location. The horizontal line at z = 0, the horizontal region at z = 0, so there is no line, sorry, but you can see here at z = 0, that's the location of the equatorial plane for rotation of the pulsar. And so the red lines are basically unsuccessful particles, which were injected but just advected in the downstream towards the right-hand side, because the fluid flow is from the left to the right. And the blue ones are actually the interesting particle trajectories. So you can see, so these are those that were able to gain energy in our simulations because they managed to cross at least once, to do at least one cycle and cross and recross at least once the termination shock. So the blue ones on the left-hand side, you see that they're basically ejected due to drift motions on the shock surface, further away from the z equals 0 when they re-enter the upstream, and then they go back into the downstream at greater absolute values of z. So this is not good for particle acceleration because there is less turbulence in the downstream at these regions where the absolute value of z equals 0 is greater in our simulation as well as in MHD simulation. So the particles basically usually do 1 or 2 cycles and then they are advected downstream without gaining much energy. However, for the electrons, or the opposite sign of charge depending on the polarity of the pulsar, but for this polarity, it's the electrons that are well accelerated in our simulations. You can see that it's the opposite situation. So basically, when the particle is, for example, here in the upstream at z positive values of z, the Lorentz force basically pushes them towards z equals 0. So it kind of focuses the particles around the plane, around the equatorial plane. Whereas when the particles crosses the plane, the B field, as you saw, flips to the opposite value. And therefore, the Lorentz force will flip to the opposite value. And that time, the Lorentz force will try to bring back again the particle upwards towards z equals 0 when the particle is at negative z. So in other words, the particles tend to spend their time on these so-called Spitzer orbits, which are basically orbits where the particle is oscillating from one side to the other of this z equals 0 plane. And the particle always re-enters the downstream in this region close to the equatorial plane, where we have in our simulations, as well as in MHD simulations of the Crab Nebula, where we expect to have the highest levels of turbulence and therefore the highest levels of particle scattering, which allows them to cross and recross very often the shock. So this allows to remove the problem for perpendicular shocks. And we see in that way that we have very efficient particle acceleration. So we calculated the resulting synchrotron spectrum. So the black line is the new star data level. The COMTEL data is with these magenta field dots, and the Fermi data is in green and orange with these green and orange dots here. You can see, so there is, so this again, this is from first principles because we really followed individual particles. We really followed their trajectories, integrating the Lorentz force in this model. So it's normal that not all of these lines fit exactly well the data, but it's quite interesting to see that a number of these different models, which depend, which basically are different realizations, which are basically our model predictions for different values of the unknown parameters, like the inclination angle between the magnetic field axis and the rotation axis of the pulsar, which we don't know for sure, or the magnetic field strength of the turbulence in the downstream, etc. So all these curves are different values of these unknown parameters, for all these different known values of these parameters. And you can see that several of them can actually provide a very reasonable fit to the observational data for the synchrotron emission. So that's quite interesting news. And also we can provide a relatively good fit of the data in inverse Compton, and especially of the PV data. You can see that most of the that actually all the models that we found are able to create PV photons. So now in the last, sorry?
2 minutes left.
Yes, in the last couple of minutes, I will just show a few things for more, let's say, advanced particle in-cell simulations. So we also did the same simulations, but with particle and in-cell simulations. So basically, compared with the previous case of unmagnetized shocks seen in the literature, where you see no strong acceleration to very high energies, we also use the same magnetic field geometry as seen on the lower right panel with this magnetic field geometry, and here in white, this null point for the magnetic field in the upstream. So again, the fluid is coming from the left-hand side towards the right-hand side. And in our simulations, we can see here, these are the results for the mean the mean Lorentz factor of the particles in the simulations, and you can see that you have actually pretty high energy particles close to the shock surface in the equatorial region being around y = 0 in this simulation. So this is this region around 1, and here in 4 behind in this region here in the shock downstream, we also get some particle acceleration via magnetic reconnection. And we calculated the particle spectra in these different regions of our peak simulations. And we confirm here that in this region 1, close to the equatorial region of the termination shock, we do get preferentially acceleration of one sign of charge, electrons here, as you can see. The electron spectrum extends to pretty high energies in our simulations. So actually they are accelerated by at least 2 orders of magnitude in terms of energies compared with the incoming energies of the particles. Here, this is the electron spectrum in blue, and in red, the positrons. And in the downstream, we see also acceleration to low energies via magnetic field, magnetic reconnection. But this is more both electrons and positrons are basically accelerated to similar energies, so there is less discrimination between the charges compared with the mechanism that we see. Compared with the first order Fermi mechanism that we see occurring at the shock surface. All right. Okay, so I will skip these details and I will go directly to the conclusions. So in these simulations, we have shown we have given the first numerical proof of electron and or positron acceleration to PeV energies at pulsar wind termination shocks. Via the first order Fermi mechanism. And we have shown that actually taking into account the large scale geometry of the transverse magnetic field in this region allows to remove the problem of particle acceleration at such shocks. And we see that we can get efficient particle acceleration in this region, equatorial region of these shocks. We can provide a pretty good fit to the X-ray and gamma ray data from the Crab Nebula, in particular, the LASSO data. And interestingly, we also see that pulsar winds probably favor one sign of charge, well, 50-50 in terms of probability, depending on the polarity of the pulsar, which is an unknown value. All right, so thank you very much for your attention. I'll stop here.
Yeah.
Thank you for the very interesting talk. You should probably see some anisotropy in the polarimetric images taken by ISP in X-rays. Did you check that?
Yes, so this is something, well, actually, this is something that I'm planning to do. Yes, this is indeed a very interesting question. So unfortunately, let's say a question which I think one point which would be even more exciting is if it were possible to have the circular polarization and not just the linear polarization, because with the circular polarization, you could test indeed a very important part of our model, which is preferential acceleration of one sign over the other sign of charge. But unfortunately, getting circular polarization data will wait quite some time before one is able to do this observationally.
Gwenaël, nice talk, thank you. My question's about turbulence fed from upstream. In your baseline model, it's very laminar. Your structure's very laminar. Even in your PIC simulations, you seem to have a very low level of turbulence upstream. How destructive is turbulence in dealing with this effect that you're identifying?
All right, so what we found, so in the first type of simulations, the test particle simulations that I have shown, actually the actual strength of the turbulence in the upstream that we put by hand in the upstream is not very important. The only important thing is that we have just a little bit of a turbulence so that the particles do not remain indefinitely on SPICE orbits. Otherwise, they will outrun infinitely the shock and they will never come back into the upstream. This is just a minor, let's say, technical detail. But whatever the level that we use, as long as it's very small compared with the level of the regular field in the upstream, we check that our results do not change in terms of particle spectra and maximum particle energy. Now, in terms of peak simulations, we actually do not add any turbulence in the upstream at the beginning, so the flow is really laminar. And what happens in that case for the particles to return in the downstream is actually more complicated. So I do not have time to discuss the details, but actually what we find is that there is a very low density. So this is the shock surface here that you can see here. The upstream is here on the left-hand side. And there is naturally a small cavity of very low density fluid, but very high density of high energy electrons, so high energy accelerated electrons, that forms in this cavity around the equatorial region of the shock. And the particles basically are not anymore accelerated by crossing and recrossing the shock itself, but it's accelerated just in this region by shear flow acceleration in the downstream, in the back region of this cavity. So it's accelerated in the fluid movements just in the back of the cavity. It sees a pretty high minus V cross V electric fields in this region, which allows it to be accelerated to very high energies. So in that case, it does not need any turbulence in the upstream.
Thank you very much. Let's thank Bruno again.
All right. Thank you very much for your questions and for the invitation.
Next speaker is Silvia Celli. She'll talk about non-thermal emission from young massive star clusters.
Yes, okay. So, good afternoon, everyone. The content of the talk would be concerning gamma ray and neutrino prediction from young and massive stellar cluster, in particular, those detected recently by the Gaia satellite. So this is the outline of the talk. Well, let's say I will go very rapidly on introducing you why star clusters are interesting particle accelerators, because Luigi already introduced us about the available observation in very energy, ultra energy gamma rays. So what I will focus on is how did we model the particle acceleration in the young star cluster, in particular, considering acceleration at the wind termination shock blown by the collective wind of the cluster, and the contribution from supernova explosion occurring inside of the cluster as it ages. And then we will go through the data release 2 of the Gaia satellite to explore the sample of known clusters in our galaxy. And I will show you our predicted hadronic emission from this sample of objects. And in particular, I will conclude with detection prospect for CDA, LASO, and KM3net with neutrinos. So very rapidly, we have a bunch of observation in very high energy gamma rays, which indicate that star cluster can accelerate up to, this is tens of TeV, as seen by Hess in a few objects in our galaxy, but even up to PeV, as was observed by LASO, at least in one of such clusters, the Cygnus cocoon. Now, you might wonder what is powering the high energy emission that we see from these objects. And in principle, we expect the different contributions. So at first, when the cluster is very young, with an age below 3 million years, we expect that the acceleration occur at the termination shock of the collective wind. Why 3 million years? Because this is basically, as you see here, the lifetime of the most massive star in the main sequence observed in our galaxy. Okay, so this is the age when the first most massive star will start to explode into supernovae, and so at some point the supernovae energy will start to power actually the star cluster up to an age that we expect to be of the order of 30 million years, which is when an 8 solar mass star would explode into a supernova. This is for solar metallicity values, but okay, so in principle, we expect very young clusters to be powered by termination shocks of the collective wind, and clusters with age, let's say between 3 and 30 million years, to be powered by supernovae. Okay, and then at some point, all of the acceleration power will fade out. So in terms of geometry, the young star clusters, those that are powered uniquely by the acceleration at the wind termination shock, are expected to be like this. So we have at the center the core that embeds the hundreds of very massive stars which blow a wind, which is terminated here. So this is basically where the run pressure of the wind equals the pressure of the bubble, and then you have the supersonic wind is also driving a forward shock into the interstellar medium. And the typical sizes of this system, so for the termination shock of the wind, we should consider something like 20-50 parsec, and the bubble sizes are very large, of the order of hundreds of parsecs. Okay, so why we consider wind termination shock as particle accelerators for two main reasons. So the first reason comes from the observation of an overabundance of neon-22 in cosmic ray composition, which suggests that to some extent, we need to accelerate to explain cosmic ray composition. At least part of cosmic rays should be accelerated from matter which gets ejected from winds of stars, because this is where of massive stars where you produce neon-22 in the 3 alpha chain. Another reason comes from actually hydro and MHD simulations of these systems, which shows, I know it's maybe very hard to see for you, but here this is a simulation of a star cluster. The core is just a couple of parsec, and all around it you see a shock. Here the color scale shows you the Mach number of the shock. So this termination shock, which is blowing by the collective effect of the stars, is actually a strong shock with Mach number of order of 10. So we expect this to be an accelerator. So people have been trying to model how the particle acceleration and wind termination shock might work, and they solve basically the stationary transport equation you see in spherical symmetry. So this is, of course, a limitation of the model that it assumes isotropical distribution of particles. So the solution of this equation was obtained with the wind velocity profile at this geometrical setup that I've described so far, with two boundary conditions: that the net flux of particle at the center of the bubble is zero, and also that outside of the bubble the distribution function of cosmic rays matches the galactic cosmic rays. Okay, so we started from the solution that people found from this model, and of course it comes with a few assumptions. In particular, you should assume what is the fraction of wind power that is converted into cosmic rays and into magnetic turbulence, and also what is the diffusion coefficient where the particle would propagate, which is the main uncertainty of the model, which is the reason why we explore different possibility, either a Kolmogorov-like or Bohm-like or a Krajnek-like diffusion coefficient. So the solution of the transport in at the acceleration at the wind termination shock, you see, is a power law essentially, with exponential cutoff, which are due to the confinement inside the bubble and the escape from the upstream of the wind termination shock. But as you see, what people have found with the characteristic value of wind luminosity for these clusters is that actually theoretically it is feasible to accelerate particles up to PeV in the case that the diffusion proceeds in the Krykman or bomb domain. So basically, what is the main difference between wind termination shock, acceleration at wind termination shock and isolated supernova remnant is basically difference in how the maximum energy is achieved. In the case of supernova remnants, you have transient phenomena, so time-limited acceleration, and with characteristic values of radius and magnetic field at this system, we expect maximum energy at the level of 100 TeV. On the other hand, this is obtained by Hillas condition, so confinement of particle in the shock size. With wind termination shock, we actually do not have time limited because these are stationary systems living for millions of years, but rather space limited acceleration. And so in this case, the large bubble sizes can maybe allow the system to achieve PeV energies. So we wanted to test this sort of models with realistic system of clusters observed in our galaxy. You see here, well, the data release 2 from the Gaia collaboration of a couple of years ago has collected about 2,000 clusters in our galaxy, and 400 of these are young in our definition, which means, let's say, with age smaller than 30 million years, so candidate for particle accelerators. You see the distribution of these clusters in the galaxy shown here. This is the position of the sun, and then the color scale gives you the age of these clusters. So you see that clearly this is not a complete sample for the entire of our galaxy. It is complete within a couple of kiloparsec from us, so it's still a subsample of the real distribution of clusters in our galaxy. The point with now we did a great effort in trying to move from the observed properties, individual properties of stars inside these clusters, and translate these properties into the parameters of the cosmic ray acceleration model that we need, and in particular the wind luminosity. So I don't have time to go through this, so I'll go very quickly. You see here, basically, we mostly assume that all the stars inside of the cluster are main sequence stars. And so, of course, we obtain wind luminosity values, which are just lower limits to the real cluster power. Okay, this is something you should bear in mind. But we found out that there are some interesting, very luminous cluster at the level of 10 to 38 erg per second, which is to some extent the level that was used from our colleagues to demonstrate the PeV acceleration in the system. One of the other great uncertainty in this kind of modeling, when you want to get to gamma ray emission, is how the gas distribution is made inside of the system. So we have this sort of profile where you have the cold wind inside of the wind termination shock, this low density bubble, and then a highly compressed shell. This is a standard scenario to some extent, but in principle, there are cases in which a shell, at least when the cluster ages, fragments, and this can give you a sort of overdensity also inside of the bubble. So since we have characterized the full, let's say, stellar content of each cluster, we can also, assuming solar metallicity evolution, compute the expected number of supernovae occurring in the cluster. I will go very quickly just to mentioning you that we include the supernova contribution in these clusters, and what we find out in terms of maximum energies for each cluster is that actually you see here the maximum energy achieved at the wind termination shock and at the supernova explosion inside of the same cluster. And I draw the lines at PeV energies just to show you that there are cases, in fact, in which we expect these clusters to operate as PeV accelerators. And so here there is a list that we added in our paper with the maximum energy is expected to be provided according to the level of diffusion that operates in the region. And so I think it is very interesting to go and explore this sort of systems. Let me go really in 1 minute to show you that you see the large uncertainty which is driven by all of the effects that I have been describing to you, how they reflect into the spectrum of gamma ray emission expected from cluster. This is from Westerlund 1. And in most of the cases, this is in Westerlund 2, we require the shape of the spectrum to require some most likely bomb diffusion to operate in these systems. And just to conclude, but maybe I was, it is blocked. So there were a few, okay, let me go just here to the integral sensitivities. Because you see here the CTA expected sensitivity, and all of these are the clusters that are part of the Gaia catalog. So north, CTA north for left side and CTA south for right side. So in principle, we will be able in the very next future to probe the level of emission that we are predicting from this system. And in the bomb diffusion case, there is a more extended population that might be targeted by CTA. Okay, so let me leave you with my conclusion and I'll take your question. Thank you.
Thank you very much. It's time for one quick question.
So I see that Cygnus wasn't included because it wasn't in the catalog, but within the framework of your model, could the gamma rays from Cygnus be explained simply by supernovae or?
Simply from supernovae? Oh, this is a good question. I'm not sure whether people have been doing this. I mean, I know Brian has worked on this. I know people have tried to explain the emission with the wind termination shock, and this seems to be in principle feasible, but I think, at least from what I recall, these people were not including the supernovae contribution. I don't know, Brian, did you do this, the supernovae contribution in Cygnus? Okay, so maybe in the next hour you will have the reply.
Yeah, I can comment a little bit on that. Within the Hawk paper on the Cygnus region, the model was just stellar winds, and that gave a pretty good feed to the data. So, I mean, we didn't have the need to incorporate supernova or things like that.
Yeah, I think that with regards to the age, it should be 4 million years, Cygnus. So 4 million years, it means that perhaps some supernovae have started to operate in there. Maybe it's not the dominant component yet, but in principle, some should already be there. But I'm not sure whether people have done this. So we can check it.
All right. Let's thank Silvia again.
Thank you.
The talk by Natalie Matchett has been moved to the next session. So for Natalie's talk, please come back after the poster session at coffee break. For the last talk, I hope you're not arachnophobic, because Christoph Findler will talk about VHG emission from spider binaries.
So while they're looking for the slides, let me start off by saying there was a bit of a hiatus and I got back into modeling this stuff. So when you create a code, it's like a little baby and you know everything about it and you nurture it and you love it. And then you send it off to school and your collaborators work with it and you get it back and it's a teenager and it's raging. So I've been trying to re-understand the code and see what's new and why and so on. So I'll take you on a bit of a journey to explain. We've come to understand some of what's happening, but still looking. So it's a progress report. And I would be happy for your patience as well with that. Let's hope they find it. Good. There we go. Okay. So yes, the focus is TV, but it's also multi-wavelength and broadband sources, and we think that we might expect orbitally modulated TV photons from these systems. So that makes them very interesting. So just a bit of science, background, motivation. I'm a pulsar guy, so I've worked with his people on the Vela pulsar, and we got a very, very exciting result published recently about 20 TV pulsed photons coming from Vela. Now, this challenges the models. I think we can get there, but it's a tight constraint. So this is a very new thing, and we've been kind of thinking what this might mean. So in the context of this talk, we also are looking for other novel sources that we can probe the pulsar winds and the wind composition, the shock physics, acceleration processes, and interaction. And spider binaries are such a source class. So another motivation is that they are showing up in bigger numbers. If you look at the 3PC, which is the Fermi Third Pulsar catalog, there's about 50 spiders now. And when Fermi discovers these things, that initiates a multi-wavelength follow-up, and through synergies, they discover more and more of these systems. And I'll talk a little bit about the multi-wavelength signatures that we see from these types of sources, very interesting. So there are labs of very interesting physics and rich phenomenology that they display. And there's a lot of interesting science that one can get out of this, I suppose, with lots of hard work. But in principle, one can study the evolutionary link between transitional pulsars and how they form, maybe. There is a cycle scenario, and also particles coming from these sources like leptonic cosmic rays, also equation of state constraints, because many of these pulsars embedded in these binaries are very heavy, and maybe even thinking about PTA signs and FRB signs. So what are spider binaries? Don't be scared, as Marcus says. They are actually in analogy to what you find in nature, and some people challenged me on this and say it's a myth. And I had a look and I saw, well, it does happen rarely, and it can be either way. It can be the female or the male eating the partner, so it is scary. But yeah, we see that the pulsar has a very intense wind of particles and photons, and initiates a wind on the companion by heating the companion. And then these two winds can collide and create an interbinary shock. And so you can see flares on the companion star. You can also see that there must be, we believe, acceleration of particles to very high energies at the shock site. And you get two flavors, at least two, the black widows and the redbacks. And so the black widows are the lower mass companions, and then the redbacks, the more energetic ones, and the higher mass companions. So you see a lot of interesting signatures across the waveband. For example, if you read this plot, it's actually an eclipse. It's a delay on this axis, so it looks like opposite of an eclipse, but it's an eclipse. And you see that if you are at some type of orbital phase, the radio emission from the pulsar disappears. And it's a function of frequency, with lower frequencies having a wider eclipse. So this is also telling you that there is some obscuring matter that obscures the pulse from the pulsar. This is another newer result showing the same thing. And there's a frequency dependence again, that you can see the width of the eclipse changing with frequency. And this gives you kind of a schematic for what's happening when you see a pulsar and a companion, and there's a shock obscuring the pulsed signal from the pulsar. Optically, you have a heated companion surface. So by fitting models to this light curve that you measure, you can really constrain the inclination angle. And together with the radio pulsations, you can constrain the masses of the systems. And also you find that the temperatures that you need is in the order of thousands to 10,000s of Kelvin, which gives you a lot of soft photons that you can upscatter with TV particles to find, hopefully, TV gamma rays. So the X-rays, we see power loss in the spectrum extending up to 80 kV, for example, which leads to estimates of shock B fields of the order of 1 Gauss. And you also see this double structure, which we think is a Doppler boosted synchrotron. So for example, if the pulsar is there schematically and the shock is around the pulsar, then this would be pointing away from the observer. This is the companion. And in opposite case, so like in the redback case that we are discussing today, if the shock is around the pulsar, it's pointing towards us. When you hit this emission, you see a peak in a modulated emission at the orbital period in the X-rays. And we believe that you might see something similar in the TeV gamma rays. Very interestingly, Clark et al. Had an idea, and they thought, well, why don't we look for eclipses in the gamma rays in the Fermi GeV band? And they looked at almost 50 millisecond pulsars and the spider binaries, and they found eclipses actually. And this constrains this inclination angle and gives you nice robust limits on the mass of the pulsar. So that was very interesting. And so there's been a lot of modeling, and just to show that it's this relation between the two winds. If the one is stronger than the other one, it overpowers the other one, and you can either have the shock around the companion or around the pulsar, and that will show up in terms of the phasing of the light curves that you see. And just to one slide, people with peak codes have also started looking at this, and they are finding interesting results. So we have a more of a traditional approach of parametric modeling and then radiation physics. So the new thing is that we've inserted new shocks. The first initiation of this code instantiation was a spherical shock, and now we have a shock with a tail, or a Wilkins shock so-called, or even a Cantu shock. And these are well-known results, analytic results, where you have an R of theta that comes from balance of momenta. So we wanted to see what that would do to the code. And so we solve a particle transport equation. I will not go through all the math, but we do the energetics, we do the injection, we have this parametric exponential power law, and then we solve. What we do is to solve for the minimum and the energy and the normalization of the skew by looking at energetics arguments. So then there's beaming, and again, not boring you with the math, we kind of do a lot of transformations to include the inclination angle and the rotation of this binary period of the star, and also Doppler boosting. That's what gives you the nice peaks in your results. And so then the headache started, because I had to just get back into code versions, and I will not bore you with all this stuff, but it took me quite a few late evenings, new energy grids, parameter combinations, remember what you've done, what you've not done, what you've missed. And first, when I turned this on, the flux was down by 20 orders. And then we realized, oh yeah, shucks, we need to remember that there's a dimension to this problem, and we have to be careful. And then it was fixed mostly. So then we were looking for 2 or 3 orders. So that was not too bad. So the question is then, okay, so for the calibration part, for the spherical shock, we found quite good calibration. You can see these are different zones and different quantities, and without the details, don't worry about them. We have good calibration for the spherical shock, at least. So now we can go into the new thing. There's slight new discrepancies, but it's just newer implementations to optimize the code and looking at grids. So we're still looking into that, but that's not too worrisome. What was a bit worrisome was when we turned on the different shocks, but I'll get to that in a moment. We updated the synchrotron kernel. There's this nice paper by McCloy 2000 where they say that they can do this using Chebyshev polynomials, and you don't have to read this from a table, and you get slight improvement and smoother SR spectra. It's not a huge effect, but it's good to improve these things. We also have new injection spectra, either a power law or a cutoff or a broken power law. And these, of course, give you some different predictions. There's the synchrotron emission and the inverse Compton. And we're always hoping to be close to the Hess sensitivity so we can hopefully provide motivation to look for these sources and for the modulation in the TeV band. And by having X-ray data, we can constrain certain things, break degeneracies, and have a more robust idea of what's going to happen in the TeV band. It's not perfect, but then if you add your light curves, you can see that there's, at least in the model, some different options. This is just for the injection spectrum changes, but there's a lot of other things you can change, a whole slew of parameters. We try to use what's in the literature and to combine these things, make it as robust as possible. But there is a bit of uncertainty, so we always try to make it better. And this was the first result I found. And I thought, oh, where's my flux gone? There's a song that says, where have all the flowers gone? So where's all my flux gone? But I realized after long searching that I think it's just a beaming effect. And to test the hypothesis, I played and I plotted, oh, you see also the effect on the light curves of the different shock shapes. And the beta is just the opening, it determines the opening of the shock. So it's very narrow or very open. It's the ratio of the momentum fluxes of the two winds. So what I've done is to then plot for the different shocks in all these colors, different inclinations. And you can see in the next few that I'm going to flip by that this moves around a lot. So in principle, it means that there's a degeneracy between the shock shape and the inclination angle. But then looking at the light curves, you can really then constrain and break the degeneracy potentially. So that's our hope. So there's a few things to do. We want to double check our injection spectra just to make sure we have the right fluxes. Check the time scales. There's new flow terms, and we need to figure out if nabla.v is done correctly. There's some grid changes, and also we want to see if this beaming is really true. So what we are proposing, we've done this in the past, but we will redo it for this code, is to plot the so-called sky maps, where you have the inclination versus orbital phase. And if you make a cut, you see that you see actually the double peak structure. And if you go down, you see one peak, and if you go down, you can see nothing. So this would tell you the whole structure and how it's beamed, and it will give us hopefully a bit of more peace of mind. So in conclusion, these things are very interesting and promising targets, also in terms of not X-rays only and GVs, but TVs, hopefully. We have been looking with HES. We are still looking, so stay tuned for that. We are trying to improve the model bit by bit and understanding, making friends again with the teenager. So it's happening, so it's good. And we are looking for new sources now to probe the pulsar wind. So what we find, it's kind of obvious, but nearby sources, energetic sources, flaring sources, those are the brightest ones for HES and for TV, for CTA as well. And there's a lot of follow-up things one can do. If you add spectral components and you also study the eclipses, the companion heating, you can even study polarization, which will help with the B field structure and the local interstellar spectrum, the cosmic rays from these things. Thanks a lot.
Thank you very much. Questions for Christopher? Brian?
Okay, so I won't ask you about the modeling. I'll ask you a very naive question. In the beginning, you showed the eclipse of 1957 with the radio eclipse.
Okay.
You flipped very, very quickly, and it looked like the eclipse is consistent on the one side when it goes into eclipse, but it's not. It's varying when it comes.
It's asymmetric, right? Yes.
But it doesn't seem. I'm presuming it's at different dates, right? So it seems that when the pulsar goes into eclipse, it's very similar, but coming out, it's behaving differently. I'm just wondering why.
Yeah, I don't think people know exactly. It probably just points to dynamic nature of the intervening material. And the radio signal is very sensitive to the intervening material, possibly. Yeah. Brian, is a difficult one. Okay.
All right, then let's thank Christo and all the speakers of the session. Okay. And we'll reconvene at 3:30 for the last session of today. Wait. Oh, it's on. We're just gonna wait for 5 more minutes to start the session. Okay. Yeah. Yeah.
And then
Okay, so I'm
when do they start?
Yeah. So who's starting? Yeah. So it's
somewhere randomly.
all right. So I need to know. Yeah, this has zero cancer response.
So I'm right in front of you.
Right.
Yeah.
Okay. Cool.
Okay, you're Brian. Okay. The last one. Okay.
I'm Brian.
Yeah, Brian. Hi, Brian. Am I on? Yeah.
So you have 30 minutes and I can take as long as I want.
Yeah. Just wait for like a couple of more minutes because we left for the coffee a little bit late and the posters. I think the posters off this focus meeting. So
Yeah.
yeah, there's.
It's because of the web because by the time you find the poster you're interested to talk about, and I'm gonna go back.
Yeah, it's quite short. It's not sure. Get coffee and then go to school and come back.
The poster number don't match the screens downstairs. Kind of like
Yeah, yeah, true.
okay.
Okay. Right.
This place was so long about it. Yeah, something coming up. It's far from there. So like, oh, I saw that thing, but hold on, yeah.
Eu sou voluntário, então, tipo assim, se você quiser, eu fico mic running aqui, mas é que ele só tem um microfone, então é com você. Bom, essas a gente está dando quanto tempo? Bom, tem meia hora, né? É isso.
Right. Okay. Yeah, no, I think most of them are so, so is there yeah, please. So yeah. No, it's not good for you.
Quando scrive a Paolo nota che segue dalla e dipende da lei proprio un po' di questi dei vostri.
Esse negócio aqui a gente consegue ligar?
Ele controla, ele não liga e controla, então em princípio.
Vou avisar sempre 5 minutos antes do tempo final. Sim, Okay, hi everyone. So welcome back to our second afternoon session of our focus meeting. So I'm Ion Viana from University of São Paulo. I'll be chairing the session. And the first talk of the session is by Brian Reville. So please, Brian, I think you can go on the podium. I'll let you know when you have 5 minutes left on your.
Okay. So thank you to the invitation to speak. And it's great to be here in Cape Town. So a lot of the topics that I wanted to talk about have been covered today. So I'm hoping I can probably yield some of my time and get us back on track, but famous last words. Okay, so I run a group in Max Planck Institute for Nuclear Physics, where we work on particle acceleration theory. And so I wanted to talk about some of the main topics of interest that we're working on, and very much related to the topics we were talking today. In the last few years, and a major focus of this specific meeting, the attention has really shifted to the highest energy cosmic rays. This is because the best known feature, or let's say the one specific feature that's desirable to obtain, is at this few 10 to the 15 electron volts. And so we all know this story, and we've heard it several times today. Cosmic rays are hard to figure out where they come from because they have short mean free path in the galaxy. So we try to look at gamma ray signatures to figure out where they come from. Two things: we measure these beautiful power laws, and so therefore we look for power laws in the sky. Fortunately, we see lots of them, particularly with the aid of instruments like Hawk, LASSO, and of course then all the IACTs. Standard argument of power, the power in cosmic rays, to maintain a steady state, you need something that can provide 10 to the 41 ergs per second. One thing that I really want to highlight is that cosmic rays, there's this big range between the knee and the ankle. So above the ankle, we know they're extragalactic because they're almost isotropic, and the gyro scale is comparable to the scale height of the galaxy. But there's this big gap between the knee and the ankle, and just getting so-called pevitrons is not really enough. Yeah, because if you get protons to a PeV, you can really only get iron up to Z times that, so close to 30 PeV, and that's just not sufficient. We know you need to be getting up to close to 10 to the 18. Okay, so gifts from nature, you all know this. We look for the radiative signatures, either of accelerated protons or nuclei, or electrons, and nature has been very kind in giving us many such sources and trying to interpret these. Of course, and what the observations are telling us about these sources is where I like to realm. So I don't need to go through this. There are many different ways, or two primary ways of doing ground-based gamma ray astronomy. In many ways, they're highly complementary, and exploiting that is again something that is the main focus of this meeting. Okay, and so what are turning out as let's say the most interesting and somewhat new and unexpected sources. So the particular ones which we've seen many times already today is a Cygnus cocoon, but we have other sources like microquasars, which were briefly mentioned today for Hawk detection of SS433, and this is something that's really quite new as well. Okay, supernova remnants has been around for a long time, but again, we're still trying to understand what they really do. And then we have these very extreme accelerators with these high spin down power pulsars. So the Crab being a very excellent example. And Gwenaël covered a lot of what I wanted to say about that anyway. Okay, so I'm going to make the case for supernova remnant shocks. We heard several talks this morning saying that they're not good enough. I disagree. Supernova remnant shocks are probably still the dominant source of cosmic rays in the galaxy. I don't see any way around that. Okay, you can put special requirements on the environments they're going off in, but they're definitely the dominant contributor to cosmic rays in the galaxy. There's simply nothing else that can realistically provide the required energy. We see them. We know they accelerate particles. More specifically, we can associate very strong emission around the shock and not so much ahead of it, which means something is confining these particles to the shocks. And therefore, if they try to get out of the shock, they get bounced back and forth. This is diffusive shock acceleration. Okay, so it's a natural consequence of basically if particles try to escape, they will self-confine. And understanding that process is key to understanding the maximum energy. But one of the beautiful results of diffusive shock acceleration, non-relativistic shocks, is that it has this very, very simple prediction in the simplest possible scenario of a single power law, something like e to the -4 or p to the -4 or e to the -2 if you plot it in number density. Again, which is very, very consistent with many observations. So there's very strong arguments to stick with the supernova paradigm. Okay, but this is where the problem, and I guess one of the main focus of the meeting is that where are the so-called pevitrons? Yeah. An acceleration to above PeV turns out to be hard. Here's a collection of, it's an old paper now, but by Stefan Funk. Sorry, there's no credit here. Showing collection. There was more recent figures of this, but showing gamma ray spectra of many sources, and we see cutoffs happening at maybe 10 TeV in most of them, or at lower energies, suggesting that cosmic rays are not getting to the knee. And this perhaps shouldn't be a surprise. If it were easy to accelerate particles up to the knee energy, then the knee probably wouldn't be there at all. It will be somewhere else. Okay, and so the take-home message of what we currently think is happening is that most supernovae appear to be past their prime. Now, whether that's true or not, we don't know for sure. Okay, so the question will be, if they were accelerating in the past, how effective were they, and what sets the maximum energy? And so to get some insight into this, I go even lower in energy to the younger, let's say, less energetic cousins of supernovas, just novae. So where you have an explosion on the surface of a white dwarf, accreting off a red giant. And this is actually a nice analog system for supernova remnants, because when you have this thermonuclear runaway happening on the surface of the white dwarf, it launches this shock which moves up in a bipolar outflow orthogonal to the plane of the orbit. And this shock here can move at several thousand kilometers per second, and it's going into quite a dense wind. So it's like a scaled down toy core collapse supernova in many ways. Okay, and so we recently had a very exciting event. So this was the first ever TV detected nova, or Ophiuchi, which has a few thousand kilometers per second wind, shock going into a moderate mass loss, so moderately dense environment. And so what we saw with Ophiuchi was this nice time-dependent evolution of the spectrum happening on days timescale. Right, so you're really seeing particle acceleration in action, something which you can't really do, or at least not at the highest energies, with supernovae. Okay, and so the idea was very simple. You just have diffusive shock acceleration happening at the shocks out here, bouncing back and forth, and then eventually colliding. This is with hadronic model, colliding with the dense material in the happening here, the shocked ejecta, or the shocked wind rather, and accelerating particles up. So our highest energy data point here on the fifth night was at about a TeV, or just was a TeV exactly, and therefore there must be 10 TeV or several TeV particles there. Okay, and then the interesting thing is that for any realistic model of the external environment, this maximum energy, you cannot account for it with just the potential across the source. You need to have some magnetic field amplification. And this, I think, was the first time that we were really able to show this conclusively. Okay, and it also opened up this entire field. Now we know these sources are TeV emitters, and we know that there is a much closer recurring nova, very similar conditions to our Ophiuchi, which is expected to go off in the next few months. Okay, and so all eyes will be on this, and it will really test the limits of our existing theories. Okay, and so let me try to briefly explain what those existing theories are, and what we'll be trying to look for. Okay, so this is a digression into some very, very basic plasma physics. So if I imagine I have a shock over here somewhere off to the left of the screen, and I have absolutely no turbulence in the background, particle would simply whiz along the any particle that gets kicked up into the non-thermal energy range simply moves upstream, generates a strong electric current. This current will apply a force on the background, and ignoring various small order terms, we see that we have a nice expression for what you would take two neighboring field lines and you would just push them apart. And if we want to get so-called Bohm diffusion, we need to separate these field lines essentially by a gyro radius in that magnetic field. If that's the case, particle forgets where it's going after one gyration. This is what Bohm diffusion means. And so we can make a simple energetic argument and say the energy flux carried by this, which is related to the current, is some fraction of the energy being processed by the shock. And we can just sup this in here and rearrange. And what you get is that the gyro radius, the maximum energy, is U over C times the shock radius. And this is the Hillis limit, basically. Okay. But one has to be careful. This is the strength of the magnetic field. We've just pushed two field lines apart. So this is not magnetic field amplification. This is just generating structure on the scale of the gyro radius. Okay. So if we want to go beyond that, which we need to do to explain the emission from our Ophiuchi, we need something different. And so this is what we think is the dominant effect in most high Mach number shocks. Okay, so this is just
don't want to go too much detail here. So this is effectively a growth rate of a plasma instability. So I have this current going through the upstream medium, and it's driving an instability. Now, what I showed you on the previous slide was up here, right? So these are wavelengths. So here's wavelength or inverse wavelength on the x-axis and growth rate on this axis here. So if I want to generate fluctuations on this scale here, which corresponds to my maximum energy particles, it happens about 6 or 7 orders of magnitude longer time scale than what's happening up here. So I'm growing stuff very, very fast on very short time scales. And so you know that this is where you're putting all the energy into the magnetic field, but you want this to influence up here. Okay. And you don't have so much of these timescales for a fluid element to cross the shock or to be overtaken by the shock. So you really are relying on this doing all of the work. Now, fortunately, this is very easy to simulate in a standard MHD code. And so you just plug this into an MHD code, and away you go. It's from Tony Bell, 2004. It seems to have fallen off. And the thing that you notice is that very quickly the fields grow to the size of the box. The bigger you make the box, it'll always grow to the size of that box. Okay, so it's a very, very, in some sense, easy numerical problem. In another sense, it's quite challenging because you need to get this multi-scale stuff going in. Here were some later simulations that were a bit more sophisticated. So again, similar to this, but the feedback on the cosmic rays was included self-consistently. And what you start to notice is that the magnetic field, so this is at early times, it's all very weak. Magnetic field is between 1 and 2, if its initial value, and then it gets blown up to a factor of 30 or more, right, in localized regions. But those localized regions are they're not so compact, right? They're quite big. And in fact, the cosmic rays that were driving this instability would actually scatter through almost 90 degrees in interacting with one of these blobs. Okay, so you introduce quite a specific sort of what we call hard sphere scattering or large angle scattering diffusion model is required. Okay, so what's clear is that you need to have enough of these growth times, again, at these highest energy, so you're not doing anything at these very long wavelengths, you're doing everything at these short wavelengths, but getting 5, 10 of them seems to be sufficient. And what happens is that you simply just generate very, very large scale structures or these scatterers. Picture's not fully clear yet, but what they do then is self-confined. And so they do what we need. And you can play around with the numbers. It's a very straightforward game to play, and you can work out the maximum energy. This is broadly consistent with observations. So if we have given ISM density, typical efficiency of cosmic ray acceleration, shock velocity, age, etc., agrees quite well with what's happening here, but doesn't depend on the magnetic field. The magnetic field is hidden in this confinement limit, so having enough growth times. What you can play around with, and this is what we think is happening, is that we can make this very, very large if we're in a core collapse supernova remnant, where you have a very, very strong, high mass loss rate. And so if you change the model for the density here to a simple wind model, then this rho goes as 1 over r squared. So the r and the t more or less cancel. And you get this maximum energy prediction here, where in theory, you might start to get quite close to a PeV, okay, or slightly above. Okay, and so how does this apply to our Ophiuchi? Well, if you plug in the numbers that we expect for red giant winds, you get a maximum energy that's about 5 or so TeV. You can tweak these numbers a little bit. And so it seems that this is exactly what's happening and can account for the observations of our Ophiuchi. And so again, this next T Coriolis B will really tell us what's happening. Okay, so what does this mean for supernova remnants? Well, supernova remnants, most of them are core collapse supernova remnants. These guys here, 1BCs and type 2s, and they're not going to have them. Basically, this is the sound speed, and you know the winds have to be supersonic, so you can't really make this any lower. You could make this slightly higher, but in rather extreme cases, like luminous blue variables, but then they're very rare. And so you need this very high shock velocity, very high mass loss rate, slow wind, and then in theory, you might be able to get up to a few PeV. But as I said at the beginning, that's not really going to account for getting all the way up to the extragalactic component. Okay, so we need to have another look at this. And so different options. So we've heard this already today, so I can probably go through at a reasonable pace. So the first option that we're thinking of is that it's young massive stellar clusters. So we already heard several talks. Here's some massive stellar clusters in optical and X-rays, and here's in gamma rays from Hess. And so the simple picture is that you have some star formation or massive stars driving winds here in the center. They drive a collective outflow, which terminates in a larger scale shock. Then you have this big super bubble or low density bubble, and then some external medium that's swept up. Okay, so this is the spherical cow model. There's strong motivation for this. We've seen this figure already several times today. Evidence that we are extending up above a PeV in the photons, all localized in this region, and hints that it's around Cygnus OB2. So we've been doing quite a bit of work on trying to understand what's really happening in these clusters and where are the possible acceleration sites. So hopefully this works. So is this second one going to work? Okay. Oh, okay. So you can't really see. Okay. So this was global. This is the larger scale. So we put about 50 stars in the center in a very, very compact region, each driving their own wind. The winds collide. And here's a zoom in into the center. These are supposed to be co-evolving. And what you start to see is indeed the winds merge and drive this large scale termination shock that Sylvia was talking about earlier. It's a little bit messier than this spherical cow model, and you can imagine if the stars were distributed much more over a much larger region, then this would get messier and messier. And in fact, at some point, you don't produce a wind termination shock. But in the case of Westland 1, Hess seems to indicate that could well be the case. So Westland 1 has about 1,000 stars all packed into this little star here. And then on very large scales, about 30 parsecs, you see this shell-type structure. This is probably where you have active particle acceleration going on due to something like reflective wind. Although I personally think that what's happening here is leptonic, it's not hadronic at all. You can ask me why. Okay, so what are the different possible? There are many places to accelerate particles in these young massive stellar clusters. So you can have at the outer shock itself, it's big, but it's slow. So the maximum energy is not really going to be even getting up to beyond 100 TeV. You can have a supernova remnant going off sort of in the rarefied medium, in the low density. Again, that's going to just be like a standard isolated supernova remnant. You'd be lucky if you got anywhere near to a PeV. You have the wind termination shock of the compact cluster. Again, here, I would argue you would need very, very favorable conditions to even get to a PeV there as well. You can have hydrodynamic turbulence in the shell. People have looked at this in the past. This is even less effective. So best case scenario, you might get up to several hundred TeV. But then there's one preferred candidate. It's my favorite, or was my favorite. And that's if you have a supernova remnant inside a compact stellar cluster. Because what happens there is you have all of these winds plowing into one another. They're all magnetized winds, but they don't have to be so strongly magnetized. And then you drive this turbulent dynamo, which amplifies the magnetic field up. So equipartition magnetic fields are close to about 100 microgauss inside the core. And then as they're expanding out in the wind, they're falling off quite slowly, but then BR, which is the term that's important for the acceleration, there's that combination, is more or less constant. And so if you can drive a fast shock, so fast shock that gets very quickly into the wind, can move at tens of thousands of kilometers per second, sweep up this external medium in a pre-magnetized, very special location. In theory, you might be able to get up to about 10 parsecs, 10 PeV, right, at an isolated supernova remnant. So it's just in a special location. So this requires these supernova remnants going off in very young and very compact cores. Okay. Where does Cygnus OB2 fit in this picture? So we had a series of papers that published this year where we simulated something very similar to Cygnus OB. So the power in Cygnus OB2 is dominated by basically 3 very powerful Wolf-Rayet stars and 5 powerful O stars, each having somewhere in the order of I mean, the O star is closer to 10 to 37, the Wolf-Rayet star is slightly larger. And each one of those stars has more or less the same amount of power as all the other stars combined, right? So there's another 60 stars or so. But they're distributed, as you can see, quite uniformly over this very large volume. And so you don't drive a collective wind termination shock. And if you try to look at, so another paper by Thibault earlier in the year, Thibault Vieux, if you look at isolated little accelerators in the region, They might get up to tens of TeV, or even possibly 100 TeV at the most powerful Wolf-Rayet stars, but there's nothing that we can identify in Cygnus OB2 that would really getting you up to beyond PV. Okay, and so I think certainly Cygnus X3 is likely to be a very powerful PV source, so in the field of view. But a lot of these we don't know where they're coming from. Okay, and I think the answer is my suspicion is that it is related to a supernova remnant, but we haven't been able to identify one yet. Okay, but it's a very, very complicated region, and we're reanalyzing the gas maps in many ways. So there's a lot more work to be done for Cygnus OB, and it really is a fascinating source. Okay, what we also did last year was very similar to what Sylvia spoke about. We took the Gaia catalog and tried to isolate which of these clusters that you can identify in the local region, which would meet our requirements for young and compact. So that's these red guys here, and it's about 16% of all clusters that are detectable. And so if we extend this to a more global model of the galaxy, and do a simple leaky box model, and I say simple, okay, there's a lot going in here, but it's not so there's not so many free parameters, and the free parameters that do exist are fairly well constrained, because we always think that supernova remnants are about 10% efficient. So we can here see, so here's the data, and I've broken it up here into three components. One is what we call cosmic rays from loose clusters. So these you can think of as isolated supernova remnants. They may be getting up to 100 TeV or thereabouts, and then cutting off. This is all particle. Yeah? And then you have the contribution from the wind termination shocks. It's giving you this bit here, which just helps us smooth it out here a little bit near the knee. And then we have this component coming from these very fast supernova remnants in the compact clusters. And in theory, then again, the all particle spectrum, it's going up here to maybe 10 PeV, and then heavier nuclei getting you all the way up to the transition. And then we just took an extragalactic component up here. And you can see you can get a nice global fit to the full galactic cosmic ray spectrum. Okay, so I think this is a promising direction. But again, it is reliant on this notion that you can really get these powerful supernova remnants with the right conditions. And so that's something we're currently still working on now with very large hydro and MHD simulations with my group. Okay, so another option, which has again emerged in the last few years, and sorry, I removed a slide. This was really thanks to HAWK. So HAWK were the ones that made us realize that these microquasars are incredibly effective accelerators. And before, we hadn't been looking at so deeply. So this is the famous microquasar SS433 with its iconic precessing jet. On the left is the Hess image, and it just plops right there into the center. And what you see is that these hot gamma ray emission are really coming from this narrow region that will be well inside the angle of these precessing jets, which indicates that there is some very effective accelerator located just here where these X-ray jets switch on, and there's a lot of TeV emission. Okay, and the interesting thing is, of course, that we do not see any cutoff in the Hess spectrum, which allows us to place a lower limit on the energy of emitting particles. So particles must be accelerated up to several hundred TeV. Okay. One thing that we can say, because what we have enough statistics with Hess, that we can do energy-dependent morphology, and this allows us to essentially confirm that this is all inverse Compton emission that we're seeing. All right, because you see the highest energy gamma rays are concentrated near the site of acceleration, which we think is a shock located here, again supported by X-ray observations, and then it tends to move away, so you cooling over longer time scales. And so while this is clearly showing that you have lots of relativistic electrons, we know the jets of SS433 are heavy, and so there should be a lot of nuclei in this area as well. So we should also have very effective hadronic acceleration. There's just not a lot of target gas nearby to emit. Okay, and so why the acceleration occurs at this location and why it is so efficient, because it really is one of the most efficient accelerators in the galaxy, we don't know in terms of maximum energy. Okay, and this is really starting to become an exciting area. We're starting to see more and more. So Hawk again to the rescue has detected another microquasar, and I have heard that there are many expected from LASSO as well. Okay. This brings me on then to the last. I could probably skip over a lot of this because Gwenaël covered it quite nicely in his talk. So for the case of pulsars, which are the other very, very bright, powerful sources that dominate, pulsar wind nebula dominate the ultra high energy and the very high energy sky. Most of these sources contain relativistic shocks, and I'm a firm believer that shocks are a great way to accelerate particles. People have claimed for quite some time that relativistic shocks are not very effective accelerators. I think Gwenaël covered this in a lot more detail than I did, but the basic idea is that any bending of the magnetic field in the shock frame just gets Lorentz boosted up, so you get perpendicular shocks, and a particle essentially just has an E cross B drift which drags it away, or it's gyrating in the field and the field is being swept. That's right. But I argue that nature always finds a way. So one possibility is that the magnetic field is just very weak. Self-excited fields overcome this. So here is measurement of the turbulent magnetic field, the density, and what you see is, well, you can't see it here, but this is the resulting particle spectrum. You can get this thermal bump here in the shock in the downstream, and then you get this power law tail extending, and the longer you can run these simulations, the longer to higher energy you achieve. But it scales very slowly. It only scales as the square root of time. So it's very, very slow. And in fact, it's too slow to account for most of the observations that we see of, for example, pulsars, right? Cooling would kill you, right? So you really need to have it accelerating at very, very close to the gyro rate. But it's important to keep in mind that these PIC simulations, I think this is the longest PIC simulation ever run, and it's about a second. Okay, so it's not very astrophysically relevant. But as Gwenaël nicely explained, nature always finds a way. And what we had ignored in most of these previous works was the fact that particles can get on these very favorable trajectories, which will allow particles to return to the shock. So you don't have to rely on just having all this small angle scattering, which is very, very ineffective. And so this was demonstrated quite nicely, and as Gwenaël showed, can in theory account for PV gamma rays that have been seen, or multi-PV gamma rays that are seen by the crab. I wanted to just extend a little bit on Gwenaël's picture because, and also to make the connection with microquasars, is that this is quite a generic feature. Okay, you know all of these systems. If I can talk in plasma physics terms, you know these are all current carrying systems, and J is curl B. So you know the divergence of a curl is always zero. So you must have current closure. Systems have to have closed currents, and so if you have the current going out in one way, they have to be coming back in the other way, and something has to provide these currents. And I would say that you will always find a way to get species of one charge to tap into that current. So in the case of the crab, Gwenaël's model in the equatorial region, it's these Spicer drifts which will provide this current to along your current sheet to allow you to get these particles back to the shock. But the same thing will happen actually on the poles, because you have the magnetic field being wound up along the poles, the same way that you have like Blanford-Snack launched jets. Yeah, so you have helical fields launched up, and so on axis you'll have a null. And curvature drifts behave in a very similar way close to this null as the Spicer orbits. So actually, as a particle at large radii would simply be trapped on a magnetic field and wander around on that magnetic field. But as you get closer and closer to the equator, they try to conserve their angular momentum, and then they get this very large drift. And it can actually move very, very, in fact, on the axis, it's moving at the speed of light. Okay. And so this is a way, again, that you can get particles re-interacting with the shock many, many times, also on the poles. Okay, and so one of my students did some Monte Carlo simulations of this, and indeed found that if you have strong scattering, you get nice, well-known power law, and then depending on the charge, when you have this weak scattering, you can introduce higher energy particles, and again with a different power law, but this is to do with the scattering model. Okay, so to conclude, I think we're making a lot of progress, and particularly in the last few years, largely based on new experimental results, new observations, which has been a really exciting time to work. I think it's pushing forth very, very rapidly. And I think although we're very far from a complete picture, a global picture is still emerging. I'm still confident that supernova remnants are dominating the bulk, and maybe some twist that we haven't expected yet. So a lot to be done in the coming years. And we have now competing models for the very highest energies. Again, more and more data. So I think with existing and future facilities, we're guaranteed a very bright future. Thank you.
Thank you, Brian. Time for one or two quick questions.
Yeah, thanks for the nice overview. So I had also, even though I haven't really worked a lot on pevatrons, I've also been a bit skeptical towards stellar winds and favorable. I mean, I didn't really understand why people are so quick to give up supernova remnants, mainly because if those stellar winds are accelerating hadrons, they should also accelerate electrons, and we should see synchrotron emission, which is, I think, we see from most established accelerators. Then you mentioned that one of the gamma rays from the stellar cluster might be interpreted as leptonic. Is that what you said?
Right.
Yeah.
For Westland 1, it's very hard to account for the morphology with a hadronic model, simply because advection will dominate. So you know that these superbubbles have this advection that's moving things out, and so why it's actually so small is the problem. If you know that they're stuck on this flow that's moving out, and then you would expect there to be the TV emission to be over a much larger radius. So it's basically cooling limited as it goes downstream with the flow.
Then should you expect to see correlated X-ray or radio synchrotron emission? Is that
So we looked at Eve or Zeta, we looked at everything. So nothing has been seen so far.
Okay.
So we're still looking, but
okay.
Sadly, no.
I have one question. So you mentioned that, and you showed one result where you have supernova inside clusters, and you showed that you actually managed to fit that. But what about the frequency that you need to have those supernovas so that you can have some kind of continuous injection of these PV particles? Can you comment about that?
So, I mean, if you think about it, all of these massive stars, and certainly the ones that produce the big core clock supernova remnants, are going to be born in some sort of close to their region. They don't live very long, so they're not going to get very far. So I would argue that most of these core clock supernova remnants should be occurring in this, at least a large fraction. I can't remember the exact number. We gave a number in the paper, but we're doing a little bit of guesswork and extrapolating based on local.
But you need supernovas, and you need a very fast shock also. So that happens only through a very short period of the.
Well, you have to remember you're going into a very low density environment, because this collective wind is quite low density. So if you can get them out to the edge of the cluster, where beyond the half mass radius, then in principle they can maintain a high. We hope they can maintain a high velocity.
All right. Okay, thank you. So thanks Brian again, and now we have Lucas. To contribute the talk.
Well, all right.
I'd like to know when you have 5 minutes left. Okay.
Okay. Yeah. So good afternoon, everyone. My name is Lucas. I'm a PhD student from the University of São Paulo in Brazil. We'll be talking about CR bounce diffusion today. This work has been submitted to APJ, and if you want to take a look at our early version of our paper, you can use the QR code. So let's begin with the observations. Several people already talked about these today. So very high energy emission come from extended sources up to TeV photons. These could be an indication of pevatrons, cosmic sources that spread cosmic rays to PV energies. And this observation suggests that diffusion coefficient, so a measure of the average displacements of the particle away from the source, can be up to 2 orders of magnitude lower than the average for the ISM. And the thing is that usual approach of the quasi-linear theory that you use cannot explain this. So quasi-linear theory is basically a first order perturbation and has two major problems. It cannot explain changes in direction of the particles, and the simulations do not match the predictions of the theory, and people have been trying to figure out ways to explain these problems. So in the case of the pulsar wind nebulae, I'll refer to this review by Feng. He proposed a few scenarios to explain this slow diffusion. In our work here today, we will be exploring mirror diffusion as proposed by Lazar in SHU 2021. In SHU 2021, using a few simple assumptions, she managed to she studied a case for IC443, which is an interaction between supernova remnant and molecular cloud, and she showed that the standard model would predict a suppressed CR spectrum, and with mirror diffusion, she could reproduce the observations. So to get to mirror diffusion, we need to consider a few ingredients. So first, the ISM turbulence. So the big power law in the sky. We know that we have turbulence all the way from interstellar median fluctuations to subparsec scales, but usually with pointing toward a universal origin of the turbulence coming usually assumed from supernova or the spiral arms. But we also have magnetic fields, and this leads to this relation over here. So the cascading of the turbulence is different depending on the direction of the magnetic field, and in the perpendicular direction we expect a Kolmogorov cascade. So this will lead us to an important ingredient for this work, which is the super diffusion of the magnetic field lines. So the dispersion of the field lines should follow this relation over here, and it basically is that as we follow the lines, they will disperse, and this effect over here is similar to a Richard diffusion for particles in a turbulent media, as studied by in 2011, and this effect has also been extensively studied in other works in the literature. So the other important ingredient is in the name, so we need magnetic mirrors, which also can be produced by the MHD turbulence. Mirrors are well known in plasma physics, and as the particle interacts with the mirror, the relation between its momentum and the magnetic field strength should follow this relation, and this allows us to establish a critical value for which the pitch angles of the particle, so here will be considered the cosine of the pitch angle, so the angle between the velocity and the magnetic field. We can establish a critical value to which the particle should be subjected to interacting with these mirrors. So when we combine these two effects, we have mirror diffusion. So particles should then follow the lines, and they can diffuse perpendicular to the magnetic field due to the super diffusion. But when they find mirrors, they will not be trapped between mirrors, but due to super diffusion, they will continue to diffuse perpendicular to the field, and this can slow down the diffusion parallel to the magnetic field. So these are the main ingredients, and now let's talk a little bit about our results. So we used we'll be using as a background previous simulations of molecular clouds, so turbulent MHD turbulence. We'll be using only a single snapshot of the turbulent box with fault self-gravity. These will be supersonic and subaphanic. And as a note, we are not comparing with other works that are also trying to understand this is lower diffusion, other effects that can arise. So, for instance, Kempsky and Lemon. For these works, please see Zhang and Shu 2024. They have similar environments where we can compare mirror diffusion and the effects they see, which actually happen will be present in subaphanic turbulence. So we consider two magnetic field configurations. One with the complete magnetic field, so with all the perturbations that came out of our snapshot, and another one where we smoothed out the small scale perturbations. The idea being that we wanted to reduce the effect of scattering and be able to see what mirrors are doing to the particles. We are simply computing the Lorentz force along the trajectory of the particle and seeing how it interacts with the magnetic field. This will be our initial condition, so just the Larmor radius and the pitch angle, we have these statistics. This difference in particles is just to improve for these smoothed models. The statistics for these smoothed models, and here the k smooth we are referring is like k equals 5. So above that we are trying to reduce the perturbations. So this is an example. So here we have a particle that we let it put it in with a certain initial pitch angle. You can see that it will follow at some point. It will interact with the mirrors. It continues to diffuse perpendicular and escapes escapes again and will follow until it finds another mirror. We can take a look at the evolution of this particle. So all these plots here, we have time and first pitch angle, parallel displacement to the magnetic field, and the adiabatic invariant, which should be conserved. So the relation between the momentum and the strength of the magnetic field. You can see that here when it's here's the smoothed model on the left, on the right the complete model. You can see that when state trapped, we have the conservation of the invariant, and but in the complete case, it's a bit more problematic because we have some fast variation due to scattering. We can take a zoom in this picture. Still the same models, just cut here. I added below the strength of the magnetic field. When you look at this smoothed model, we can clearly see the correlation between the maximums of the field with the change in direction. But in the complete model, this is a lot harder. We have a lot of formation in the middle, and as the arrows here are pointing, there are some points that we have bounces, but we cannot see them, or we just identify it as wrong in the wrong place because of the let's say noise in the middle. We can look at these red dots here, which are sorry, I forgot to say here. These are just mu b. We are considering where the bounce begins. And we can use this as a proxy of the interaction of the particle with the mirror. And then we can we can look at how this is distributed with respect to the critical value of the pitch angle for each mirror. So you can see that these particles here are mostly falling. So any blue blob below this line here shouldn't be considered a bounce. But we have numerical errors, and as I said, the scattering makes it harder. But still, the general trend is that it follows the expectations. In the smoothed model, especially here, we have the Larmor radius is smaller than the dissipation scale of the turbulence, and then it's a lot easier to see these here. Still, these areas below the line are not as relevant statistically as the part below where it follows. So let's finally take a look at what kind of diffusion coefficients we get from these. So here we scaled their models to a 3-parsec box, and we are simply seeing how the particles are moving away inside along the magnetic field lines. You can see that we reach here a plateau here where the particles reach a diffusive regime. There's some difference at the beginning depending on the initial pitch angle, but still we are getting values around up to 2 × 10⁻² square centimeters per second. If we look at the average mu of these models, all models reach by the end in the plateau, we reach average mu of 0.5, which is in the here I'm using as an indication of where the if we look at the histogram of mu, we see a isotropic distribution of mu. So, and also we see the conservation of the average adiabatic invariant. So we have a distribution of mu, the interaction of the mirrors. So now for this smoothed model is a bit more complicated. it's really hard to explain this result in only one slide. So if you're interested to see to understand better what is happening here, please come talk to me after the session, or you can also look at our paper. But since we have a reduced scattering, we also have less small mirror structures because we cannot separate one of the other. So what happens here is that we only have the large scale mirrors, which still can yield up to 3 times to 28 square centimeters per second for the diffusion coefficient. It's higher than the previous case, but this is because in this case, like, we have this interaction with the turbulence. We need to understand like where the Lyman radius is, the comparison between the Lyman radius and the dissipation scale, and this is basically the reason why these values here is higher than before. But so we can actually rescale our system with these equations on the left here. And to compare to systems, I'll call your attention to these 2 columns here. So basically, up here is the for a few configurations of magnetic field and the size of the system, and what values of energy and the general diffusion coefficients we are obtaining. And here below here we have the observations, and as you can see, we are able to this effect could help explain the observations we have from Pulsar Wind Nebula. And well, these are my conclusions. So I don't know how much, I didn't pay attention how much time I have. So, but I'll leave you with them. So if you have any questions, I'll be happy to answer. Thank you.
Thank you, Lucas. Do we have any questions from the audience? No? Do we have any questions from online? No? I think it was very clear. Thanks a lot, Lucas, again.
Thank you.
Yeah. So, now I think we have a online contribution by Martin. Is Martin there? Yeah. Okay. So let's put his slides and then we can start.
Okay, so hello everyone. So should I share or you will put the slides?
I think you need to, yeah, you
Okay.
share so that you
Okay,
can
I'll share.
skip the slides. Yeah.
Good. So you should see the slides now.
Yeah, we are seeing the slides, so I'll let you know when you have 5 minutes left. Okay.
Okay.
Knowing
thank you
that
very
the 5
much.
minutes is the time that normally we have for questions. So if you eat up on the questions, then we don't have time for questions. Okay.
Sure.
Thank you.
Yeah. Okay.
Go ahead.
So thank you. So I want to talk about the detection of the Crab Nebula with the TIGER experiment and with a single ICT of the TIGER experiment. On the first slide, you see a shorter author list than would be usual for the TIGER collaboration. TIGER is called the Tunka Advanced Instrument for Gamma Ray and Cosmic Ray Astrophysics. And the results I'm presenting here are basically the work from the PhD thesis of Michael Blank, and was also published in monthly notices using data up to 2021. Now, we all know what the situation is for a German-Russian collaboration. Right now, our institutional collaboration is frozen. So that's why we only have this work here up to 2021 data, and since 22 we didn't have either manpower or yeah, actually the manpower was the main problem to further work on that subject. So TIGER is a complex located in the Tunka Valley in Siberia. And there will be a talk on the TIGER experiment tomorrow by Nikolai Budniev in the same focus meeting. So I'll refer to that a few times during this talk. The Tunka Valley also hosts the famous Tunka 133 cosmic ray experiment. and it's 675 meters above sea level. What you see here, oh, I think the arrow has shifted. It should be here, the arrow. I'm sorry. So for some reason, the arrow
was wondering, that's not even Russia.
exactly has shifted away from Siberia, but it should be here. You see there is a small telescope icon. So probably in the last version, I was moving the map and this has messed up. I'm sorry. So the arrow should point here. We are at 50 kilometers to the west of the Lake Baikal. So this is a satellite image taken from Google Earth with some icons indicating the position of stations and some icons indicating the position of telescopes. The Irkut River is meandering around the site. Yeah, this is, oh, sorry. And just for the scale to understand the scale, this is a kilometer. So the icons are not to scale, of course. They're just showing the positions. And the width here is roughly a kilometer side length. Tiger is a hybrid experiment consisting of 3 components. We have the Tiger High Score integrating Acherenkov array, or you can also call it a timing array. So the last status in 21, while this work was done, was 120 stations. We, in this presentation, are going to talk about only ICT1 data. However, there are in total 3 ICTs operational. They were gradually taken into operation, the last one in 21, and ICT number 4 is going to be operational by the end of the year. We also have a muon detector. So these are surface and underground particle detectors, but these are not a subject of this talk. And as I said before, Nikolai Budnev will give a talk on the whole array tomorrow. So the Acherenkov approach that we are taking is only using these 2 air shower components, the high-score timing array and the monoscopic IACTs, imaging Acherenkov telescopes. And what we are looking at is a cost-efficient instrumentation of large areas by combining the angular resolution and the core resolution from the timing array with the monoscopic image shape provided by the telescopes. And so then we want to combine the strengths of both techniques, introducing a hybrid scaled width and also doing image recovery and correction. So how does that work? The hybrid reconstruction, the idea is that basically, if you look at the classical way like Hess is doing, or any stereoscopic system is doing reconstruction, the basic principle is that you have 2 telescopes at least, which must be located inside the light pool of the air shower on the ground. And at the energies that we consider up to 100 TeV, we have a typical distance between the telescopes of 350 meters, because that would be the width of the light pool on the ground at these energies. If you go to lower energies, the light pool is smaller. So that means that the light pool is basically, in a stereoscopic analysis, telling you how far you can put your telescopes apart from each other. Meaning that the total area that you instrument using the stereoscopic technique, so I probably don't need to explain this, but this is the major axis intersection, and you need 2 images from 2 telescopes to do this in order to reconstruct the core and the direction. So the light pool is restricting the total distance and therefore restricting the total area that you can instrument with a certain number of telescopes. With the hybrid imaging and timing technique, what we want to do is to only use 1 telescope in monoscopic mode combined with the high score stations, so that the high score stations are actually providing the core position and the direction. And then you use this core position in order to scale the image, and then you have your scaled image shape or image width and length, and you can do your gamma hadron separation with that. So as a consequence, you can place the telescopes up to 1,000 meters apart from each other. You don't need as many telescopes, and instead you fill in the gaps between the telescopes with high score stations, which are more cost effective. So that's the principle. Now, in principle, now I have to go a step back because I was talking about the hybrid idea, but this talk is not about hybrid results, because the first step towards a hybrid analysis is, of course, to understand the telescopes. Or this is the second step, because we already did the first step to understand the stations. And I think that also Nikolai Budnev will go into details on that. So here is the second Tiger ICT. This is a photograph of the second Tiger ICT. These telescopes are 4-meter class telescopes, 34 glass mirrors, and we're using a manual facet adjustment because it's not so many mirrors, so we can use a manual adjustment. We don't need motors. 500 to 600 PMTs roughly, a 15 millimeter cathode area, and the single pixel aperture is 0.36 degrees. Now the energy threshold is governed by the diameter of the dish, but also the altitude that I mentioned before is only 675 meters above sea level, and therefore the threshold is slightly larger than comparable telescopes such as the former Hagra CT system or CT1. So in the next slides, I will present some comparisons of data in Monte Carlo. So these are the airshower simulations we used. Corsica detector simulation is adapted from Centauri, and we use a classical approach of simulating protons, helium, nitrogen, and iron. So here are the first comparisons. So what you see is basically the legend is always the same. In blue, you see the Hadron Monte Carlo, meaning it's a mix of these elements weighted with a model. What we use is the Polygonato model by Hörandl. And in orange is the data crosses. The orange crosses are the data. And we also have data envelopes. Unfortunately, you don't see the difference between the 50% and the 90% data envelope because the grayscales are not really good. I mean, at least on my screen, I don't see that. So let's just say that the gray area is the 90% data envelope, giving you an idea about the spread. So the first plot here is the second hottest pixel. This is arbitrary units, so it's frequency distribution of the second hottest pixel. You see that data in Monte Carlo match quite well. The same is shown here for the length of the image with a nice match between Monte Carlo and data as well. So we have more parameters that we investigated there, and we are very confident that the telescopes are understood on the Monte Carlo level. So the single ICT data that we have used is from 2019 to 2021. There's a typo here, sorry. And as mentioned before, this is not hybrid data, it's just one IACT, and it was a publication here by only German institutes. So at some point in 22, we decided to, we had a paper in the pipeline, a joint paper of the whole collaboration with 2 different analyses, and then we decided to split publications, and this is the result. The analysis is based on a Python package, scikit-learn. The input for the random forest algorithm are the Hillas parameters: width, length, size, concentration, the nominal distance, number of pixels, and the third moment along the major axis. Then we implemented 2 regressors for the direction, or for the disk from which the direction is calculated, and for the energy, a classifier for the particle type. So that's what you see here. It's the parameter gamma-ness, and you see again a comparison between data on Monte Carlo and also the Monte Carlo of photons here in green. So
5 minutes, Matt.
Okay, thanks.
Sorry. Okay.
And the high-level analysis is carried out with gamma pi. Okay, so here you see the results of the signal from the Crab Nebula, 85 hours of lifetime corrected selected data. The average zenith angle is a little bit higher for the Crab Nebula here. It's 33.5 degrees, so the threshold is at 6 TeV. So this is the excess. You can clearly see the excess here. There will be more results on the Crab Nebula using more data, as well as also on the Makarian 421 in tomorrow's talk by Kolya. The energy spectrum was obtained from a forward folding method within gamma pi. We needed the point spread function, effective area, energy, migration matrix. This was provided by PyIRF. Yeah, so if I didn't write it here, but the power law best fit is roughly 2.7 spectral index with an error of 0.2. So here comes my summary, or part 1 of the summary. We took steps towards a hybrid analysis. The ICT data signal was just shown in this plot, in this talk, and there were some results from Andrea Porelli in his PhD thesis on high score data. And of course, please also refer to the talk by Kolja tomorrow. That will also actually include some hybrid analysis results. And then we have here outlook number 2. So the sensitivity estimate for the prototype of 1 square kilometers is shown here. So we are at the same level as HAWK in 3000 hours. Now, of course, it is very difficult to compare these sensitivities because we have to take into consideration that we have different fields of views in one single experiment. HiScore has a very large field of view. The telescopes only have a 10-degree diameter field of view. So it's always a little bit difficult to compare these sensitivities with other experiments. One thing that is important for our experiment is that for source identification and morphology and spectroscopy, we have a good angular resolution and a good energy resolution. So that's it. Thank you very much.
Thank you. Thank you, Martin. Do we have any questions from the room? I have a question, since we are also interested in these instruments such as SWGO and HAWK. These type of, you mentioned that one of the positive sides of Taiga is that it's very cost effective. Was there any proposal, or is it interesting, or would it be interesting to build this type of detectors together with the water Cherenkov telescopes such as HAWK or SWGO, LHASO, etc., or even within CTA or something like that? Like, would it help the detection somehow?
Right. So for HAWK, as you can see from the sensitivity curves, you have an overlap. And if you continue drawing the curve and look at the telescope-only sensitivity curve, you would actually go down in energy, of course. You would go down below 10 TeV, right? Because as I showed, the threshold of a single telescope is at 4 TeV. So I believe that whenever you use different techniques on one site, in one experiment, you will always benefit. Of course, the big difference between HAWK and the telescope, an air Cherenkov telescope, is always the duty cycle. So you have 100%, virtually 100% duty cycle with HAWK, and the telescopes only have a duty cycle of 10% plus. Nevertheless, within these, or a little bit more, but within the duty cycle of the telescopes, you would gain, definitely. How much for HAWK? I didn't study that. However, for CTA, I think the answer is easier. I believe that a combination with CTA would make a lot of sense. It would basically be the same to combine. I mean, the Taiga idea is basically combining small-sized telescopes in the terminology of CTA. You would take the small-sized CTA telescopes and combine them with high-score stations. And this is exactly what we're trying to do. It's not exactly the small-sized telescopes that we're using, but the category of telescopes are the same. Kolja will tomorrow also talk about plans for introducing slightly larger telescopes. But the principle remains the same, that you have an IACT with the image shape and the high-score stations. And so this definitely can also be done within CTA, but this has never been tried before or never been considered in CTA before.
Okay. We have one question here in the...
Hi, Martin. It's Ulysses here.
Hi.
So, as you probably know, LHASO is now considering putting some IACTs in their site to improve basically angular resolution and performance at lower energies. And I mean, they're only going to use IACTs, but of course, the idea of combining high score stations with the IACTs is the really nice thing of being cost effective. And with given that they already have muon detectors, they can rely on that for background separation. So do you know if it was considered something like this of using shower front timing like high score for LHASO? Have you discussed these things or not really?
There have been coffee break discussions, let's say, okay? But beyond that, I don't know. I mean, maybe this would be a question for Lasso.
Okay, thank you, Martin. Let's thank Martin again. And now we have to move on. Thanks, Martin. We now have Natalie from earlier talk, who accepted to change for this timing. So whenever you're ready, I'll let you know when you have 5 minutes. Okay. Oh. Your presentation is blank, it seems. One of the other ones is blank as well. It also just didn't went blank. There it is. Okay, okay, it's there. Yeah. All right. A few minutes. That's all right.
Free State from South Africa here. So today I'll be predominantly presenting on a project we started for my master's. And so I'm going to deviate slightly from the high energy universe and talk about mainly optical observations of a gamma ray binary source. It's coming.
If you're working on Google, some stage, you must tell us next slide. Scroll down. Yeah. Yeah. Can you? Yeah. Can you put on full screen though? Is the preview on? Because the PDF is not open. It's. Best thing to do is. Okay. It's opening on the project. Yeah. And you're using Adobe or something, or the Chrome? In both? So that's strange. We can get on with. You maybe export it in PowerPoint and not PDF. Sorry for those following online. We are just having some technical problems here, so
sorry for the interruption. I'm going to be saying next slide a lot. Okay, so we're looking at the gamma ray binary HJ0632. Next slide, please. Okay, so this is just a quick overview. If you, for those of you who are not so familiar with these sources, it's a really small subgroup of high-mass binaries. There's only 9 of these systems that have been discovered to date. And as you can see that of the 9, only 3 of the compact objects have actually, we've detected some radio pulse emission. So for the other 6 systems, we do not actually know what the compact object is. It's either a black hole or a neutron star. Next slide, please. And for that reason, there are these 2 different scenarios, either the pulsar wind scenario or the microquasar scenario. So just very quickly, the microquasar scenario is then there to facilitate a black hole compact object. And then we assume that our very high energy emission from these gamma ray binary systems is produced in particles that are accelerated in our jet. Next slide, please. But since we have actually detected 3 neutron stars in 3 of the systems, we think it is much more likely that the compact objects in these systems are actually neutron stars. And so in this case, what we expect, or what we actually see in these systems, is that the pulsar wind from our young pulsar is colliding with the stellar wind from our companion object. And so, although our companion object is much bigger and has a much denser wind, it has a much lower velocity. Although it has a much lower velocity, it's got a much denser wind. And so what we see is that the shock wraps around our pulsar. And then this also fits in really nicely with our evolution life span of high mass X-ray binaries, in that we expect that these gamma ray binaries form a really short time span from between when our original zero age, the larger of our original zero age main sequence stars has undergone a supernova explosion, leaving behind a young neutron star before it has spun down enough, allowing accretion onto the surface, which will then make it a normal high mass X-ray binary. Next slide, please. Okay, so then just to look at this table again, you can also see that in these gamma ray binary systems, you've got these 2 subgroups of our companions. It's either an O-type star or a BE-type star. Next slide, please. Next slide, please. So, and then with the O-type star, this is very similar to the general picture I've already explained. Obviously, this is now within a binary system. So as we are going through, as the pulsar is orbiting our companion star, the separation is changing. And so this obviously produces modulation in the emission because our shock is changing. And so in the case of the just an O star, you just have to worry about the wind. And so you see this single peak profile. This is now repeated over 2 periods, but you have a single peak profile. Next slide, please. If you then consider the BE systems, you have to consider the effect of the circumstellar disk of our BE stars. So these are rapidly rotating stars, and so then they form this disk around themselves. And so if you have a misaligned disk in these systems, you'll see what we see, for instance, in PSRB 1259, which will hopefully be discussed in much better detail in the next talk, that you get a double peak in the light curve. And so what we assume is happening, what we know is happening, at least in PSRB 1259's case, is that our pulsar is actually passing through the disk. And then this is creating an increase in emission. Next slide, please. Okay, so if we come, wonderful. Thank you. If we get to HJ0632, it's one of these systems with a BE star, has an orbital period of 317 days, and likely has a neutron star. And so you can see in the top right-hand corner, you have the X-ray and TeV light curve showing this distinctive 2-peak structure. And so we assume then that this suggests it must have a misaligned disk with our pulsar passing through it. However, the issue actually comes in with the two proposed binary solutions. And so there are these two systems that by Cazares et al. And Moritani et al. And you can see that neither of them do a really good job of actually interpreting this disk passage through the disk. And both of them show that the phases where we get the peaks in our emission are either far away at apastron, which is where you would not expect an increase in emission, or in the case of the Moritani solution, that although your slightly fainter peak is nearer to periastron, our brighter peak is still at apastron. And you, no matter how you kind of try and align your disk, we'd expect our disk to be quite diffuse at those at that separation. So it doesn't really work for interpreting our X-ray and TV emission. And so we started this project trying to understand why is there this disparity in the two solutions. And so there is, of course, quite a difference in the methodology that was used by these two original studies. And so Cazares et al. Went about determining the radial velocities directly from the absorption lines that are formed in the photosphere. However, I will maybe point it out a bit later when I show you the spectra, that they are very broad and weak for these types of systems. And so that really complicates your radial velocity measurements. Whereas for Moritani et al., you have they measured the radial velocity or the bisector velocity from the H alpha emission line, which arises from the disk. And then I also just said that their original orbital solutions were derived from phase folded over two different periods. And as we've pointed out a little bit earlier, that since then the orbital period has been updated. Okay, so what we've done is obtained really high resolution spectra from SALT. We've covered about 70% of the orbits so far between December of 2020 and March of this year. However, we still need at least two observing semesters still to get full phase coverage. The reason for this is because of the really awkward period of 317 days, which means that we can only cover a really small segment of the orbit each year. And a much smaller new segment that we haven't yet observed. And just everything that I'm showing you now is very preliminary. Okay, so we went about two different methods of obtaining our own radial velocity measurements to kind of echo the two original methods used by Cazares et al. And Moritani et al. And so the first way was by cross-correlation of the absorption lines. However, because they're so weak, and we can point out, you can see that they're quite weak and very broad, and so this produces a very large scatter. So then what we decided to do is, if we could heavily filter these spectra in Fourier space to filter out the broader lines and maybe focus on the narrower lines that are hopefully less affected by our stellar wind, maybe we could get better results. This, however, comes with a caveat that in order to cross-correlate against large regions, which is what you want to do, we couldn't cut out all of the iron lines in our spectra, iron 2 emission lines. And so our cross-correlation does actually have some contribution from the disk still. And then just to argue that we think that actually the iron 2 lines are formed really in a more central part of the disk, at least better than where the bomber emission region is. So we think that any argument against the disk being disrupted and our iron 2 lines maybe affecting our radial velocities will be mostly negligible. And then the other method was to go and fit void profiles to our bomber emission lines. So this is due to the disk being Keplerian. And so if we focus our radial velocity measurements to the outermost part of our lines, which is obviously formed in the centralmost part of the emission region, you then get your radial velocities from the centralmost part of that region in the disk. And so this is just the results that we have so far. On the left-hand side, you can see The blue is from the cross correlation. The red is from the average of the Balmer emission lines against Cazares et al. And on the right against Moritani et al. Obviously refolded now on the newer orbital period. And you can see there's quite a significant disparity between the SALT data and what is suggested by Cazares et al., specifically since this region over here is where phase of periastron is. And so you would expect to see quite a significant deviation in the rate of velocities, which we didn't see any kind of hint of. And in the Moritani solution, while it is much more similar to what Moritani et al. Suggests, there is a hint of slight difference in the trend. And I would like to bring your attention to this gap here, which is where the expected phase of periastron is, where we expect periastron should be. And you can see even in the Moritani et al. Data, there's quite a large scatter and not actually a lot of points in this really important region. And so our best fit at this stage from Moritani et al. Is actually to data with two different trends. So we don't actually, it's not really a good explanation of what we expect our orbit to look like. And so if we also look at our latest semester of data, we can see an uptick in the trend of the SALT data. So we are interested to see what will happen in the next 2 semesters, if it will continue this trend, or what we can expect. But this obviously shows us that we do expect quite a large change in our orbital solution. Okay. To get back to the X-ray, because it is a high energy station, as mentioned, that the two peaks are likely due to the disk crossing. Another thing that we see, if you go read, there's been over 18 orbits. They've noticed that there seems to be specific cycles where the X-ray data particularly flares. And so there's this idea that the flares are also possibly due to phases where the disk has grown. So after the disk has grown, you get a flare in a particularly bright flare in the X-ray. And so in addition to the rate of velocity monitoring that we've done, we've also monitored the characteristics of our emission lines. And so just for now, we've shown the equivalent widths from our H alpha and H beta Balmer emission lines. And so the different colors represent the different orbits or semesters that we've observed. And you can see in this latest semester in red, there's a definite increase, at least in the equivalent width of H alpha. You also see that there is a change in the equivalent width from literature that they have said that in the bright cycles, the bright flare cycles, there was an increase in the equivalent width. And then you also see what appears to be, at least for now, with our very minimal amount of data, that there is orbital modulation within the equivalent width. And so we have maybe two ideas that this is some evidence to disk passage without an orbital solution. The first is that if the filter comes in, it can truncate our disk. And this then causes the disk to build up a little bit. And while it's building up a little bit, it gets slightly denser, thus increasing our equivalent width before that our disk starts to disperse a little bit again. The other idea is that maybe if our disk is much more misaligned and our pulsar just punches through and doesn't truncate it too much, is that it might irradiate the disk, and then this causes widening in our emission lines as well. So this might be some preliminary evidence of this passage. Yes. So I'll leave you then with my conclusions. Watch this space. We expect the orbital solution to change quite a lot, and that hopefully, if we get more data, we can trace the equivalent widths and get a better feel for what's happening in the circumstellar disk in this source. Thanks.
Thank you. Thank you, Natalie. Do we have any questions in the room?
Yeah, I guess the two solutions are just a set of orbital parameters. Can you fit your own solution to your data?
Yeah, so we have done that, but since we have this gap, we don't feel too confident presenting it yet. So I've played around a bit. I've also gone and fit to say now, I don't want to really cherry pick data, but if we take out some of the Mauritania points there, and then we just get a trend regardless of that large scatter there, then we have a orbital solution for that, and it is quite significantly different. And it does actually put our primary peak near periastron, which is what we want. But yes, without a full orbital, without full phase coverage, you can't really, make any conclusions. So, yeah.
Okay, let's thank again Natalie. Have to move on. Yeah, a little bit behind schedule. Now we have Brian van Solen. Yeah.
So we'll wait in anticipation to see if my talk works. It's not like anyone wants to go to supper or drinks or... Hey, it works. Okay, cool.
All right.
Okay, thanks very much, and thanks very much for the organizers. And so we started the session with Brian giving a very detailed modeling talk, and we're going to end with a different Brian giving a completely non-detailed modeling talk. And we'll be talking about observations of one source particularly, which is PSBR 1259-63, which is a high mass, which is a gamma ray binary. So this is work I've been doing mainly with Maria Cherenkova and Denis Snadashev, but a number of different collaborators that have been helping with collecting the multi-wavelength data. And so Natalie's already given a broad introduction, and I'm very much aware that everyone wants to get out of here at a reasonable time. So I will skip a lot of my introduction, but let me just point out that for these systems, they're high mass systems. So this is different to the spider binaries that was spoken about earlier by Christo. And the other thing is that in these systems, we're going to ignore the stuff like SS433, which the emission is coming from the extended jet structures. For the gamma ray binaries, the emission is all coming from the inner core. And so Natalie already covered this, but there are these two models, and basically the microquasar model doesn't really seem to work. We have, at least for 1259 specifically, we have a young pulsar in the binary system. And so all the emission that we're getting is coming from the shock front that forms around the pulsar and how this interacts with the circumstellar disk and the stellar wind from the BE type star. So I'll skip that as well. And you've already seen this table, but just again, that we have these two different distinctions between the O types and the BE types. And so we're looking here at one that has a BE star in it. So PSBR is a 3.4-year orbital cycle. So once every 3.4 years, the pulsar moves through the circumstellar disk. And we can see this because the pulsed radio emission becomes eclipsed. And so at the same time that we lose that pulsed radio emission, we start to get an increase in the non-thermal emission that's coming from the system. And the system is highly eccentric, so basically we're getting very little emission over here. There's some radio detections, but basically everything is happening over here as the pulsar goes through the circumstellar disk and is much closer in. So, I mean, it's going in from, very, very far away to like less than 1 astronomical unit from the O type, 09 type star. So coming into this, what do we know about the system? So this is the sort of multi-wavelength light curve. And if we look at X-ray this is observation since 2010 through to 2017, there's a very consistent picture of two peaks in the X-ray emission. So when the pulsar comes in the first time and then the second time, you get very consistent double peak structure in the X-ray observations. If we look at the optical, which is sort of really what I've been doing, and we've been using SALT to trace the H-alpha. So as was mentioned in the previous talk, H-alpha is a trace of what's happening in the circumstellar disk. We get an increase near the first disk crossing, which will be consistent with interactions during that time, and then a broader interaction, which is broadly in line with having tidal interactions affecting the circumstellar disk again. What's completely unexpected for the system is that Fermi-LAT starts to flare 30 days after periastron. So when all the other emission is busy turning off, so the X-ray is turning off, and the other the TV emission, which I'll show now, is also starting to turn off. The gamma ray flares, and critically it flares at more than the spin down luminosity. So this is being powered by the pulsar. We're getting more energy out, the gamma ray energies, than the pulsar is busy putting in. So if we go into this more and we look at this has been analyzed, as for example, by Tam et al., and they looked at the different periastron passages, you can see that not only is the flare occurring after about 30 days, it's occurring later. And so this is 2010 and 2014 is similar, but it's erratic. It's not occurring in the same way. In 2017, it's going up and flaring even later. The flare is here at about, starting at about 50 days after periastron. There was another paper that looked at this, Johnson et al. In 2018, and they went in and actually found the sources flaring on like down to 10-minute timescales, where the 10-minute timescale flares, which is the bottom one there, is close to 30 times the spin down luminosity from the source, so of the pulsar. So we're getting a huge amount of energy being emitted from the system. Just since we're talking about TV gamma rays, so this is the Hess-like curve that was put out from the last periastron, from the 2017 periastron passage, and it shows something slightly different. The TV emission seems to be peaking earlier. We actually have a slightly lower emission near the first disk crossing, and the higher increase then after the second disk crossing at Hess. So to try and figure out what was going on, we had a large multi-wavelength campaign over the 2021 periastron, which was back in February of, obviously, 2021. And the reason for this is it was a very favorable time to observe it. Because of this long orbital period, you want to be able to observe it at certain times of the year. And so we had a large campaign to look at this, obviously with Fermi, but also Swift. We got nicer data. We had a long-term SALT observations as well as ATCR observations around the periastron. So what are the main things that we saw from this? So firstly, it flared even later. So the gamma ray flare occurred between about 60 to 80 days after periastron. People still owe me money on the bets that this wasn't going to flare, but it occurred at a time that there is absolutely nothing happening in the X-ray radio or optical. When we looked at the X-ray, which was behaving nicely for 10 years, suddenly the X-ray had another peak at about 30 days after periastron. So we had a peak before, and so that's the first disk crossing, second disk crossing, but we suddenly had a third X-ray peak that popped up. We also then had ATCR observations, which we were tracing around the second disk crossing, and it doesn't show up quite so clearly. Sorry, there's a dashed line, which kind of goes over there. You probably can't see it so well in the slide. But basically, we had a correlation between the radio and the X-ray, which then broke at about 30 days after periastron. And so that's difficult to explain because, I mean, if they're being produced by synchrotron radiation from the same electron population, we would expect them to be changing in roughly the same way. And then lastly, if we look at the H alpha, again, we got a very similar result, except that it seemed to be consistently slightly lower. So it's a sort of low significance, but consistently seems to be slightly lower over that periastron. And then just quickly, recently, the Hess collaboration put out the newest results for the 2021 periastron as well, and they got, again, a similar result that the peak is now occurring after the disk crossing, but no indication of a change near where the Fermi flare occurred. So, and then one last thing. We also then went back and looked at the gamma ray flares at GeV and NG. So this is now 2010 to 2021. And sorry, if you just look carefully, the dates on the bottom don't quite line up. They're centered on where the flares are. And really, you're getting these minute scale flares over all the periastron passages. And just to give a sense, that line, the horizontal line, is the spin down luminosity, which means for every periastron, we're getting rapid flares. And so the question is, how do we explain not only this continuous and repetitive non-thermal emission, but also the fact that the GeV is on its own and is doing these rapid flares at all times? And so the idea that we're having is that it's probably connected to the circumstatic disk. So this, just as illustration, is SPH modeling that were done by Okazaki about 10 years ago, looking at the system. And basically, this is just for different densities of the circumstellar disk. And you can see that as the pulsar goes through, of course, the disk situation becomes extremely complicated and the material starts to break apart, right? And in fact, around the 2014 and 2017 passages, there was evidence of an X-ray blob moving out, which suggests that part of the stellar wind or part of the disk wind is being thrown out of the system. And so the idea is that the circumstellar disk is changing from periastron to periastron, and there's a huge amount of turbulence or variability that we expect from this. So what's causing modeling? And now I'm of course, very aware of all the modelers in the audience are going to question all this. But our idea that we're putting forward to this is that we have two emission zones. So we have a strong shock near the apex. And this can then be used to explain the X-ray and the TV emission, that we have the strongly shocked X-rays. But we need now also to be able to produce a high luminosity at the GeV emission and also rapid variability. And so the idea is that probably that cone is busy confining the pulsar wind, and it's directing it in the direction of the outflow. So not necessarily Doppler boosting the emission, but that the isotropic unshocked pulsar wind from the pulsar is being directed in the direction of the shock. And so we can get inverse Compton scattering from that, and that can probably then fit to the low levels of gamma of GeV emission that we get before periastron and the lower levels that we get closer to periastron, but that we need to introduce something else to produce these flares. And so if the disk is being broken up, we know that there's clumps in that material. And so those clumps can start to interact with the rapidly moving unshocked pulsar wind. We can start to get rapid emission from relativistic bremsstrahlung. And so that's what we're proposing was happening, is we're getting this extra component to produce the flares. And you can see this is what's being modeled over there. Okay. So why are we having a difference for each periastron passage? Well, we're getting this small but subtle change in the circumstellar in the HL for emission line. And so if the disk is busy changing, we know the disks of BE stars change over long-term scales. What's going to happen is the shock front is going to change, at least the opening angle of the shock is going to change. And so this will probably this will change the amount of emission that we get. And so the total GeV emission will be proportional to the cone opening angle. So if we have a larger cone opening angle, the general flux or the luminosity should be lower. Of course, this could also potentially explain why we're getting this third X-ray peak, because if the shock front is open wider, it could be interacting with the disk for longer, and any impingement onto the shock front would push it closer. That would increase the magnetic field, which could also increase the X-ray emission. So we came out of this with a number of open questions still. Why is there a correlation and then no correlation between the X-ray and the radio? Where's the X-ray emission coming from? In our model, it's not consistent with a single power law. We think this is connected to the diffs. The HL for those seems very similar. So how do we trace this? The idea would be that potentially we need to go to infrared. Elmer observations would show this. And I guess it's not really clear still, why is the TeV emission turning on so early? So it's okay, we'll get more data. So it went through periastron about a month ago. And so very briefly, these are our preliminary results. And these are extremely preliminary results. This is all our fast look, quick look analysis. So please don't cite us. But it's not doing the same thing again. So Fermi has reported 2 flares. It's now flared 20 days before periastron. But the main flare is now back to 30 days after periastron. It hasn't pushed later. The X-ray observations have flared slightly earlier, so they're consistently flared about 5 or 6 days earlier. And post-periastron, the second disk crossing is staying flat. It's a much more complicated behavior than we've seen. Based on this correlation, we've had extensive ACCA and Meerkat observations, but this sort of nice, simple linear correlation that we were expecting to find, we don't find. There's clearly no simple correlation. And preliminary looking at the SOLT data, our H alpha is also peaked slightly earlier, which suggests the pulsar is interacting with the disk earlier, and it, at least up to about 30 days, has peaked higher. It's the blue point over here. So it seems to suggest that our X-ray our disk is larger again during periastron. So what are the takeaway? It's not behaving. I don't know. It refuses to do the same thing. We're starting to make the argument that we should stop taking data because it's just making it worse. But no, okay. I think we have a good broad overview of what's happening. We clearly have to have multiple electron populations. The X-ray and the TV are probably coming from this highly shocked emission at the front of the apex of the shock that we're having, but that we're getting these orbit-to-orbit variability because the circumstellar disk is really behaving differently. And that's difficult to trace because it's occurring out at like 30 to 40 stellar radii, which is not really so easily traceable with the H-alpha and clear exactly what's happening. And so we expect to get these orbit-to-orbit variations. Of course, we're getting more data in. The radio data is still being analyzed. We're still getting more Meerkat data coming in. And so hopefully we'll be able to have more additional complications, which we can try and then explain in different ways. But thank you very much.
Thank you, Brian. Do we have any questions?
Or is that way?
No? So let me just check if we have questions online, but I don't think so. So then thank you again, Brian, and let's thank all the and let's thank then all the speakers of the session and close the session. Thank you.